warning. All right. May I have that for a moment? Before we get started, I'd like to say there'll be a little fanfare sort of 2 minutes before the end of your talk. So wrap it up, take questions. Unplug your laptop while you're taking questions so the next speaker can come up and plug his in. Introduce yourself, because I'm not gonna. And they want to know who you are out there on the interwebs. All right. If somebody asks some silly-ass question, go over to them, stand next to them. This is the internet sound. If you're not standing next to them when they ask their silly-ass question, nobody's going to hear it. And then, after you mock them, nobody will understand it. All right. The only last thing I want to say is the internet mic, don't hold it in your hand, clip it to your shirt. If you hold it in your hand, nobody's going to be able to understand what you're saying out in the world. And as important as this part of the meeting is, there's a whole other place out on the internet. All right. Thank you and welcome. And with that,
oh, I was going to use the mic because it's so attached here.
Keep babbling until...
this too. This is the internet.
Oh, all right. Ah, very well.
We'll put that there and run away.
I will be here for history now. I'm George Perry. We're going to cram this into a couple of minutes, 5 minutes. We don't like watching sausage being made, I'm told. And the same goes for politics. And that elephant thing, maybe, maybe not. But definitely net neutrality. The once and perhaps future net neutrality. I try not to use words like right and wrong and good and bad. So let's say that net neutrality and its absence will have consequences. Hi. Oh boy, look at that. So speaking of consequences. A train is leaving station B, headed west, and same time, 500 kilometers away, a train is leaving station Q, headed east on the very same track. Where they will meet, where Bitcoin and quantum computing will meet, we don't know. But I hear the price of Bitcoins is booming, ballooning, yeah. All right. If we fail to tax corporations, if we tax people, and if we eliminate an inheritance tax, this will not necessarily be a bad thing, but it will very likely mean the end of the republic as we know it and the introduction of an hereditary aristocracy. Literally, when we're in a land where money and property, if we allow the continued piling up of cash, it's not a bad thing. It's a very exciting thing. Not nearly as exciting, perhaps, as right now. John Harbold, are you ready?
No.
No, very well. I'm not mad.
Keep babbling.
Because we're still looking at our brains. Folks are sticking wires into human volunteers who start thinking about things, and we're trying to track where our thoughts lie. And where does the concept of lying lie? I'm terrified of this because we could be the centipede brought to our attention. How do we think? How may we think better? How just a little bit of tweaking could make us a much more civil species. But who tweaks? Who decides what's a little? And civility. All these questions once were answered when we were small compared to the scale of nature. Nature on Earth is still big enough to destroy us, but we're big enough to mess with ourselves. Let us not shrink from this thing. Taboo doesn't really defeat evil. Taboo merely delays our coming to grips. Meanwhile, evil is tracking us faithfully. How about now?
No.
Yeah.
Somebody reinflate him, man.
So good and bad and right and wrong. Where do these judgments lie within us? And I hear tell.
Okay, enough of your crap.
Yeah, excellent. Artificial intelligence. John Harbaugh. Yeah, this is for history, and that's for our studio audience.
Okay.
Yeah.
This one?
Yes, you don't need that one.
Thank you. Comes from having a Marine for a father. Okay, my name is John Harbaugh. I've been doing Forth for the last 38 years, off and on. And one of the things I like about Forth is its concise syntax. Also, you can use that to do a lot of other things. And I'd like to be able to show that Forth now can run Pthreads. Pthreads is a multitasking thing that you to have in one process the ability to have 2 or more threads running. And the nice thing about that is you can now write your code where you don't have to worry about switching between threads. When do I have to run this? When do I have to run that? It just so over here. Can you you can see me, right? No, that doesn't matter.
I was going to the screen. This is mine.
Okay, that's okay. See, Unix originally had processes. These are programs that run. And they're controlled under the Unix OS, but the problem is the Unix OS is very, very slow. And it's, in terms of its heavyweight, means it uses a lot of memory and a lot of time. And it's not very, that's why up until recently, there have been no real Unixes. Okay, well, it's back in the 80s, there were these things called RTOS, time operating systems. They were threads. And it was autonomous, could run, could communicate with other threads, interface through interrupts. So some bright guy thought, hey, this would be great if we could put threads within a process. And that's why it was initially called lightweight processes. But they said, let's make it shorter and call it thread. Okay. It's nice. And I like them very much. It makes programming a lot easier to do. Now, okay. To understand threads in terms of Forth, think of a thread as an independent Forth machine. It's got all its stack, the stack, the return stack, user area, things like that. But how do we get it so that each thread has its own stack and private area? Well, this is this concept called thread local storage. And it has been implemented in many C compilers, especially GCC. And what it does is you can now assign memory for each thread using its underscore thread. And what it does is it allows that variable or memory area to be replicated for all threads running. And this is what's really crucial to be able to have threads running under GForth. Okay, one of the things that's nice about threads is you can set priority, which means you can have threads that run at high priority or threads that run at a much lower priority. Also, there's a scheduling policy that you can set. The FIFO, first in, first out, basically that runs until completion. But you might have a case where you have several threads with the same priority, and you want to be able to make sure that each one gets its own execution time. Well, what it does is you can set a thread quantum, means a thread will only run for this given amount of time before it's handed off to another thread of the same priority. And they have something else called schedule other, which I have no clue what it means. So there you go. But this is nice because the way this gives you control on how you can have your threads interact with one another. Okay. When it comes to threads, you can create a thread, destroy a thread, and you can cancel a thread, meaning you can put what are called cancel stops, within your code that says if you cancel a thread, it will only stop when it gets to a certain point, to this point in your code. You can also yield a code, meaning if your thread has nothing else to do, it can say, well, I'm giving up the thread of execution, let some other thread run. You can then detach a thread, which makes it run kind of like a process in Unix. Okay. You can also compare threads if you're looking for a particular thread to make sure that it's the one you want. You can also get your own. This self means there's this data structure that I'll get into a little later that identifies what a given thread is. And also joining a thread, meaning you can have several threads running, but some of these threads can exit with status. Well, the thread that started this other thread running, you can say join, and it will wait for that particular thread to exit. All right, now each thread has this other thing called attributes. Obviously, the ones you can say is you can set its priority, again, state, policy, scheduling scope, inheritance, meaning you can have threads that get created from other threads. They can inherit the same stuff that thread has. Also, what's important is the stack size. This is not the Forth stack. This is the local area that a given thread runs out of. Okay, and you can also set what's known as a guard size, which tells you, oh, if I didn't allocate enough memory for a given stack, well, this will tell me when that happens to hit. Okay, you can also do resource locking. Things like mutexes, these are like binary semaphores. If you want to protect using a piece of hardware or a piece of memory or in fact a piece of code other threads could execute. So you can lock until a certain condition is met, and I'll be giving examples of that at a later time. There are also the read-write locks, which allows you to protect a resource from writers and readers. And then there's spin locks, and these are locks for SMP. As you know, most modern computers have many processors on them instead of just one. Okay, now, thing called the barrier. Barrier is used when you have a thread that spawns two or more threads. You have a question? No, okay. Two or more threads, and the problem is you don't know which one will exit first. The barrier, you just set the number of threads that you're waiting to complete, and then you just wait on that barrier, and then it'll just go through and wait until all those threads have completed. Then you can then do a join, because without it, you could have several joins to do, but you don't know which thread will exit first. Well, this is the one that allows you to do that. There's also signaling. These are like interrupts. So you can have threads signal one another to do certain things. You can, again, mask them. You can query, did I have a thing? You can also, now this is important. Remember, signal is not a verb in this case. Signal is a noun. To send a signal, you tell what thread you want to send it to, and then you tell the signal number, and then that'll be your way of communicating. Okay. A lot of things that Pthreads needs are pieces of memory. Some of these things are opaque. They just say create them, and then threads will initialize them at their will. There are also other things, you know, like setting timeouts. Okay, the nice thing about this is Forth has the capability of handling both. If you have just an opaque piece of memory, you can create it using the Forth word buffer colon. And then that will just, it's like, you'll see an example I'm going to show after this. Then here you can show if you have to set like a timeout, well then you have the ability to set up a C-like structure where you can set, say, like a timeout value, and it does work. Okay, this is the example. Test thread is this is going to be an independent thread that's going to run. You can see that I pass into it a return variable, some ID number, and this N is the number of things I'm going to have on the stack. And plus, I need this thread structure. I need to put that in. And what it does is, after it exits, it returns task. So what this does is, the first thing it does is it sets the data stack, and you can, I mean, the stacks in Forth. And this is the data stack, the return stack size, floating point stack, and local stack. And then what it does is, after it executes new thread 4, well, it just takes that stuff off and returns this thing called thread. And this is a bunch of other Forth stuff to get the stack to work. Then in this case, one of the things this is just some example code that I have. I can say, okay, tell me, get my thread structure, okay? And what it does, it'll put that structure on the stack. Then I said, okay, get my thread 1, get its thing there, and test to see if they're equal. And then if, I guess I have this sense backwards, sorry about that, I can tell whether the thread that I'm running is thread 1 or some other thread. Okay, now this is a loop that I have. This is where I was using to test the cancel capability. If I were to cancel this thread, this is the point at which the thread would cancel. Okay, now next, I have a mutex that I've created someplace else, and they said I want to lock that thread, meaning there could be other threads out there that are competing for the same mutex. And if it doesn't get it, then that thread goes to sleep. But if you do get it, then what it does is, because all these Pthreads calls have return values, you want to make sure you check that just in case something goes wrong. And that's what I'm doing here. And if it comes back as not 0, then I say, well, I have an error. But if everything's good, then I print out thread test, and then what I'm doing is I'm printing out what instance this thread is and what my iteration is, and here's a small delay, and here's where I unlock that thread. And then this is the error checking, and then this iteration count is where I increment it. And then let's see, what am I doing here? oh, this is if my iteration count has reached 4, then I say, okay, I'll print out a message, do some stack business, so that I leave the return value, and then do a pthread exit. And this is where the thread just goes away. All right. Now, this is where I start the thread, okay, for execution. What I do is I get the thread ID, the thread structure for this guy. I have a variable here where to receive return status, and then I say join. And here is where it will wait while that other thread is running, doing whatever nonsense it has to do. And then once it exits, then I'll be able to get the return value and be able to print it out and do whatever I need to do. Let's see. Okay, now I've also created these things pthread variable, so that all I have to do is just say, because I know how big a thread variable has to be, and I included that in this pthread variable. That will it's just like regular variable, it just creates the thing. Then here's this is where this is how this thread here will get executed. I just make sure that I put the return value here. I have instance 1, I want 2 iterations, and then this is this thread variable, so that when I run the thread, I just say this execute it and start that thread off. And then here is where I just say, okay, wait for that thread to complete. Okay. One of the things I like to do is have future work, because I really like the Forth language, and there's a lot of code that you can use. What I want to expand the pthreads vocabulary to include scheduling calls. All right. And then the next thing I want to do is something called thread pools. That's where you have, usually this is in like a large application where you have many threads running, but they're the same kind. What this thread pools will speed up execution. Also, because Forth is interactive, I want to be able to debug threads at the word level. So I can actually say debug a particular Forth word that I've created, be able to set breakpoints within it, and be able to single step, either step over a word or step into it. And because the x86 architecture has more than just its regular stuff. There's a like a DSP instructions. I would like to be able to include that and be able to use be able to incorporate GDB, so I could do debugging at assembly language level. And my real thing I really want to do is there are various RTOSs that make a distinction between a task, which is a low-level concept, versus a thread, which is a high-level. So a thread can consist of 2 or more tasks, and hopefully there will be an RTOS that will support both thread local storage and symmetric multiprocessing. And hopefully one of those is going to be coming out soon, or I'm just going to go absolutely nuts. Also, I fiddled around with creating a GUI. And the nice thing about that is there's one called Glade that runs under GTK, that's GNOME under Linux. And it's nice, it just creates, you can just use it to create what your GUI will look like. But one of the things it needs are callbacks. These are, so when you activate, click on a button or move a slider, callbacks get called. Well, I want to be able to write those callbacks in Forth. And as you can see, I kind of was right in mid-sentence when I had said, oh, I've got to get to Forth. So, any questions? I know I threw a lot out at you, but like I said, I really like the Forth. I like the concept of Forth. It's okay. Yeah, go ahead. I do right now. I do Linux, but yes, you can do what do you call it, Windows if you want. There's also, like I said, when I find an RTOS, well, we'll have another operating system that Forth will run under, and be able to use the capabilities of Forth. So yeah, go ahead.
How do you, when you release a thread?
Yes.
What do you handle memory?
No, Threads will handle the memory.
So when you release it.
Yes, it does. Yes, it takes care of all that for you. Okay, Yank, please. Oh, careful, careful, careful. Here. Okay, I've got to get this thing out of your hands. This out of here, because I don't have much battery time here. Okay, thank you guys. I got to get Sam going. Oh, God damn it.
So, while the previous speaker is wrapping up and answering questions, make your way to the front of the room if you're presenting next.
No, it's not a standard. It's there are many thread implementations.
John?
Yes. Yes, I do want to give him the mic because I was trying to keep my voice down, and everybody out there. Okay, sorry about that.
Gives us a little chance to have a little coffee.
Yeah. All right. Right now? Yeah.
You're on.
Hello, everyone. My name is Sam Falvo, and probably about 10 years ago, I came up with a way of writing Forth software that I found really improved my ability to write readable Forth. And for about 3 years, that methodology, if you will, kind of languished a little bit, and then I realized, you know what, I should probably put this up on the internet and just kind of preserve it. And that happened about 7 years ago in 2010. So I'm going to revisit that methodology today. It's called, well, back then it was declarative, imperative, then inquisitive. But I'm renaming it to declarative, inquisitive, then imperative because reasons. But before I continue, there's a gentleman on the internet. His name is Rich Hickey. He is the author of the Closure programming language. It's a Lisp dialect. But he has a particularly interesting talk where he goes into the differences between easy and hard, simple and complex. And it's interesting to see that, especially in the Forth community, we like to conflate easy and simple together. I would recommend watching this talk if for no other reason than to see that they are in fact separate concepts and may help explain in the past why Forth appeals so much to us as programmers. But since we don't have a full hour to invest in watching that video, I will just summarize here. Basically, you have simple versus complex. And Richard goes into some of the history of the words briefly. What it basically boils down to is simplex, from which we get the word simple, means one braid. In other words, you have a bunch of strings that are just kind of hanging there, and that's it. You just have a single braid of cloth, basically. Complex means that you're actually combining things. You're taking multiple braids and you're making something compound out of them, basically. As distinct from easy versus hard, easy just means with facility. It's something that is very close at hand. You don't have to exert a whole lot of effort. Hard, of course, is the opposite of that, meaning something is solid. You need a lot of effort to be able to do something with it. Which raises the interesting questions. Is Forth simple? And as with all things in life, it's complicated, right? Yes, absolutely. Forth is very simple because it allows us to write software without such things as heavy syntax, an edit, compile, run loop that requires you to wait 15 minutes to see the results of your work and so forth. On the other hand, there are other things that make Forth difficult, or not necessarily difficult, complex for people to understand. You have to constantly manage your buffers, right? And I'm not talking about, you know, blocks or anything like that. I'm talking about things like what's in pad, what's at here. Even your stacks are necessary, especially if you're not running on MISC hardware. Managing your stacks is a critical thing because you can't just, you know, you can't just recirculate the stacks, right? You actually have to drop what you leave in the stack and leave them balanced. Dynamically scoped variables, everyone's personal favorite, base. You have to preserve base and before you set it and then reset it again when you're done using it. You know, that's just additional complexity that you have to deal with. This is not necessarily a bad thing. It's just different concepts that you have to keep in mind, and you're entangling them into your program, and that's what makes Forth a more or less complex language. Along the other axis, is Forth easy? Once again, complicated, right? There are certain things that make Forth trivially easy. Again, the lack of heavy syntax allows you to focus on operational semantics of your program. This is one of the key things of all concatenative languages is we want the lexical representation of our program to, as closely as possible, match the semantics that we want. And that's something that's missing from a lot of other programming languages. So Forth definitely has a big win here. The lack of declared types. This can go in either column, but I put it here under the yes column because how many times in Java do you see something like foo equals foo, you know, and it's like you end up with this stutter in your code, and that just adds a lot of noise to your code. And I find that very annoying. This is a big one for me. Flat global environment as distinct from a hyperstatic global environment. Forth, as we know, uses a hyperstatic global environment. That basically means if I define a word, it means exactly what I mean it to mean at that point in time, right? It's a very context-sensitive thing. If I redefine it later, it takes on that new meaning without altering the previous definition for older code. Most programming languages have a flat global environment, which basically means your symbol at the global scope has one definition for all space and all time, right? So that's kind of an issue there. It's also not easy for a lot of people, right? Typed operators is a big hang-up for a lot of people. The distinction between plus, D plus, M plus, F plus, so on and so forth. Global state versus local state. I think this is more of a familiarity thing. But it is nonetheless a hang-up for most people. A lot of people are very familiar with lexical scoping rather than global scope. And then finally, DIY aggregates, right? So Forth has no aggregate structures built in, so you have to write all the things that you need yourself. This includes everything as simple as arrays, all the way up to something as complex as what I like to use, relational tables, right? So, but at least it gives you the flexibility. But again, it's something that you have to keep in mind. And a lot of beginners get hung up over that. But that's a very brief exploration as to whether or not Forth is simple, complex versus easy and hard. Let's take a quick tangent now. Convention over configuration. This is a popular term, especially became popular at about the time Ruby on Rails started happening. Basically, it's a design paradigm where you employ a learned set of conventions to minimize the amount of thinking that you have to do when you're actually writing the code. This is very different from configuration-based code. I'll give you a quick example here. So this is Oberon versus the same code in Forth. Well, it's not exactly the same code because Oberon code I ran out of space, right? So basically, the Oberon code and the Forth code, they're both simple programs. I want to make this very clear. This is using Rich Hickey's interpretation of simple versus easy, right? They both are very simple because they both do exactly one thing. It is a single concept. You're inserting a node into a list, period. You're doing. But when you look at the configuration example, basically you're making your architecture and your data schema explicit to the reader of the code, right? I've invested 10 lines of code, and we haven't actually gotten to the guts of what insert actually does. But goodness, we sure do know what that looks like in memory, at least, right? So that's a certain advantage for that. On the other hand, the Forth code is every bit as simple as the Oberon code, and it is far easier to write, okay? 2 lines of code, if you can even call them lines, right? They're so narrow and so short, you could probably get away with using just 1 line of code. However, in order to really read and understand this code, you have to visualize in your mind what the memory layout looks like, right? So this is an additional burden on the reader. So which one is actually better? Well, again, it's complicated because it depends on your application, right? This may not always be the right solution for your needs. But going back to the original point, what can we do in terms of convention? Like, how can we conventionally write Forth code in a way that allows us to not always have to keep that visualization in mind? How can we use convention to preserve what we want out of Forth code while at the same time gaining some of the additional benefits of being able to just instinctively read the code and be able to say, okay, something's happening at this point in the code, and I know it has to be here, right? How do we get that? So I came up with a system called Declarative. Originally, Declarative, Imperative, then Inquisitive. So if you do a Google search for that, you'll get some of the older documents. But Declarative, Inquisitive, then Imperative. I switched the order for a reason, which I probably will get to if I have time. But the idea is to use Forth words that fall into 3 broad categories, right? The first thing that you should really, your go-to word, if you can afford to do it, should be a declarative word. Basically, a declarative word, as I'll illustrate later, establishes a truth. I want to make that clear because that is the quintessential thing. That's what makes this whole thing work. The next thing is inquiry words, right? So these are words that ask or that interpret the current state of your program for you. And then finally, you have the Forth words that you've always been writing. These are the imperative words that actually is responsible for teaching the computer basically how to go about doing these things. So as examples of declarative words, I like to use not just nouns and verbs, but also adverbs and adjectives and past participles and all these other things. So basically, when I write my words, I like to use past tense a lot. I like to use ables. Right? There's a lot of ables in my code. So for example, readable is a precondition, right? So this would be a word that if I execute it, anything that comes after the word readable, I know definitively that whatever it is I'm looking at is in fact readable. So let's say it's a text file, for example. If I try to pass a write-only file to this word, which in Unix is possible because that would be a pipe, right? If I try to execute readable, it will detect that, hey, this is not a readable situation. I have to handle this elsewhere, right? And that's where the anomalous handling of errors comes into play. State transitions work a little bit differently. Instead of enforcing a precondition, they basically enforce a postcondition. They basically take whatever current state you have and does whatever it needs to do to establish a known good state. So, for example, if I'm reading or if I'm defining if I'm reading a configuration file, for example, parsed would be a word that basically establishes the truth that, hey, I've just reduced this complex statement, and I'm now in a state where I can move on to the next one. Likewise with undefined and defined. This is kind of an interesting example because here's a type of word that can be either a postcondition or a precondition, depending on context, right? So remember that context is a very important thing in Forth. So basically I could say colon foo, undefined, defined, semicolon. And the idea here is that the word defined would only execute if the previous variable was undefined, if that makes sense. Moving on, inquisitive words, as I said, they basically interpret the state of your program, right? They sense the state and they answer a question about it. My personal convention is I like to add a question mark to all Boolean questions. They don't always have that, but it's a general convention that I use. Also, @ signs at the end of words means fetch, obviously, right? So in this case, I'm fetching an x and y coordinate, for example. And then you have the imperative words. These are the Forth words that you've been writing for years. They operate unconditionally, right? They will, like, if I say page space page and I'm, talking to a printer, you're going to get 2 pages of paper out, right? You're as distinct from a CRT, where if I say page page, it's the same clear screen, right? So interpretation is a little bit different depending on how you define these things. Declarative and inquisitive words build on top of imperative words. So basically, what I've always been saying, you start with the foundation of imperative words, and then you kind of define a higher level interpretation of your program above. For years now, people have been saying, oh, Forth lets you write, your own specific, domain-specific languages and blah, blah, blah. This is what it is, right? This is how you do it. Declarative words may also use inquisitive words, but not vice versa. And this is almost definitional, right? If I have an inquisitive word, are you ready? And it enforces a state change somehow, then obviously it's not an inquisitive word. It has affected a state, right? Declarative, of course, can use an inquisitive word. For example, a good example of this would be, actually, let me think. Going back to when ColorForth's website was up, he had the source code for IDE driver. There was a word there, RDY, that basically waited until the IDE drive was ready for the next command. That would be an example of this, where basically you're using an inquisition. Are you ready? No? Okay, wait. Are you ready? No? Are you ready now? Yes. Okay, now we can continue, right? So this is a declarative word that definitively establishes the readiness of the IDE drive in particular. Imperative words can do whatever they want, right? This is Forth. This is your playground. So to give an example, fairly recently, so I'm working on a homemade computer called the Kestrel. Part of that is I'm going to be bringing up my own Forth environment. And part of that involves some custom applications that I'm writing in Gforth on Linux that eventually I hope to port to the Kestrel. One of these things is like a forms-based text entry thing. So if you've ever used IBM mainframes with a 3270 terminal, that's exactly the user interface look and feel that I'm going for, right? How do we replicate this in Forth? Well, I'm not going to give you the full source code here, but I am going to show you some examples of where I use Diddy to do that. This is your basic workspace definition. And now we say, okay, we want to move the cursor up. So what the natural inclination, of course, is to subtract 1 from our y coordinate, right? This works great up until the point you hit the top of the screen. What happens after that, right? So there are many ways of handling this, depending on your particular needs. In my particular case, I have to constrain this, right? So if I say up, up, for example, and I'm already at the top of the screen, I explicitly define, okay, you can't go any further. You can just stay there. So that's what this constrain word does, right? Basically, it says, if y is less than 0, then we'll cap it off at 0 and just leave it at that. So I have this established truth that no matter how many times I call up, I can never corrupt memory because I know exactly how far it goes forever. Which brings us to the formal definition of what a declarative word is. Prior to its invocation, we have an uncertain truth. After its execution, we have certain truth. If you can meet that requirement, that's a declarative word. Furthermore, if you execute this declarative word multiple times, it is idempotent because you can only establish a truth once, right? If I say this wall is white and I say this wall is white again, that doesn't alter how white this wall is. It's white, right? It's just a fundamental truth. So that's kind of how the logic works. So we can, of course, extend this to all cardinal directions, including the ability to arbitrarily set the coordinates. But the key, notice the highlighted words here, the ones in red. We handle the errors locally, right? There's no flags, there's no sentinel values, there's no exceptions being thrown. We handle it locally. This may not actually be how you want to handle the error, but at least it's handled somehow, and it's handled in a way that keeps the system running at the very least, right? I'll show you later on how we can address context-sensitive error handling if we need to, but for now, we'll keep this at this. Basically, the idea here is always handle your errors locally, because the smaller the number of controls control flow directives that you have in your code, by far the easier the code is to read and understand. Anyone who maintains a modern object-oriented program in an enterprise setting will know exactly what I'm talking about here. Okay, moving on. So we saw a case where I used a postcondition, basically a state transition declarative word. Why not use a precondition? Well, it turns out that they're not always as convenient to use. So in this particular example, I show how to do the same thing using preconditions, and already we can see that it is significantly more complex a piece of code. First of all, we involve rdrop, right? So this is one of my favorite techniques, and even I'm warning you against this, right? The ability to manipulate your return stack for non-local control flow is simultaneously a wonderful thing. I love it. I miss it every time I write in any other language. But at the same time, use it with extreme care and prejudice. Or discretion, I should say. The other thing is it introduces an if-then statement, which again is an altering control flow. And finally, we have to have a precondition for, in this particular case, for every cardinal direction. And this doesn't even address the random access ability of setting the cursor. So clearly we can see we're already at more or less double the number of lines of code. So it's not always a win. There are times when it is, though, which I'll get to a little bit later. So text output, this is fairly simple. We basically place the character into our character matrix, and then we emit it to the screen. The assumption being that the screen is a bitmap display. I don't know if you read that before, but yeah. And this, again, this is something that works really well as long as the concept of your cursor location on the bitmap screen is the same as what you think it is when you're filling out this matrix. So here's the example of where a precondition actually works out much better than a postcondition, right? If we were to enforce this logic using postconditions, we would have to replicate this at least 5 times in the code that I've shown before, right? So just be aware that preconditions and postconditions, in my experience, maybe 50-50, right? So it's you use some preconditions and you use some postconditions. They go well together, very much so. All right, keyboard handling. This is an interesting case of where declarative words are used to implement a multi-way selection, right? So the idea here is that when I handle a key, it could be a cursor key, it could be the enter key to accept the form on the screen, it could be a graphic character where I'm inserting into a field, or if it's something like a function key where I don't really care what it is, I just drop it, right? I just ignore it. Declarative words, because of how they work, effortlessly nest. I can create arbitrarily complex trees of decisions, and if I write my code, to be well factored, I can actually compose these same definitions in other parts of the program as well, right? So it increases code reuse. If I were to do the same thing in something like C, I would have to use a switch statement inside of a single function, and the unit of reuse would be that whole function. Like I couldn't just extract an excerpt of that switch statement to use elsewhere. So this is actually really handy. This comes up surprisingly frequently in at least the code that I write. So now we're actually showing an example. Here's an imperative word that basically tests to see if it's a control J for a cursor up motion, and if so, execute that up definition that we just spent the last 15 minutes on. But we would actually prefer inquisitive words. So this isn't probably a poor example because I only have 36 seconds left. But basically, we want to replace this with a inquisitive word because it allows us to fundamentally alter the meaning of that question without actually changing the structure of the code. So I'm just going to skip ahead here. Basically, once we establish a certain truth, the inquisitive word must return true for that particular condition. And likewise, if we ask it again, the same conditions should still exist, so it should continue to return true on that. Some things to notice. Definition size. I used a 2-line definition exactly once this whole presentation. Everything else has been 1 line, 1 definition. Second thing, code comprehension. This is explicitly designed so that given that you know the larger context of what you're looking at, you could extract exactly 1 definition and know what it's doing in its entirety, in complete isolation. Code locality. You will probably, as shown here, this definition of redefinition of up is context sensitive, right? So I'm redefining it where I need it. So you don't have to have 18 windows open with different source files. And then finally, everything is designed by contract, which vastly improves code reliability. And to complete, the rules of Diddy, not to be taken too literally. Like any kung fu, once you're a master at it, you're free to break the rules as you see fit. Thank you. Boy, that was close. Oh, the microphone. Let me just put this here real quick.
Okay, something. Okay, I'm Sam Chen. I'm from Taiwan. It's my honor to have talk here. And I'm with Forth about 40 years. It's interesting. Today my talk is inside of ESP32 Forth version 1.4. My
That's for the internet. This is for.
ESP32 Forth is for Wi-Fi boy ESP32, derived from ESP Forth version 4.4 on ESP8266. Two-level token threaded. A low-level program is nothing but the sequence of bytecodes. And high-level program is nothing but the sequence of CFAs of E4 word. So far, no Wi-Fi yet, only with serial. I've developed tracing mechanism and a simple debugger so that allow insight into ESP32 Forth. On boot, fully trace all words called by code, which is the main entry word in all levels, and then it gets into debugger. This is Wi-Fi boy ESP32, and this is the back side. On Arduino IDE, ESP32 Forth is set up to trace code fully. After tracing, it gets into debugger. Without tracing, it goes to quit normally. Shallow tracing could be like this. This is tracing in depth 2. Actually, the full tracing begins right after booting. Exactly, tracing begins at the CFA of code. Tracing will get to all levels of words code. Tracing ends at the CFA of quit. After tracing, it gets into debugger. With question, you'll see all the valid debugging commands. Here is the commands. Mainly, I use S to see 4 words of given name, and also use S to disassembly bytecode at given address, and D to dump 32 bytes at given address, W to show all names of 4 words defined, and N show the mnemonics of all valid bytecodes. To see a word, for example, the plus. Just type S plus. You'll see the link field, the name field, and the CFA, the code field, and the bytecodes in code field. Here is the constant word. For example, BL. The constant calculation word. For example, 1 plus. The column word. For example, here. The immediate word, for example, if. And now the word chord. It shows the versions of ESP32 Forth, and then to execute .ok. It's nothing but to show the data state and print out OK. And finally, get into quit. This is the quit. It's a query eval loop without exit. To see, for example, do $. Be careful. Here it's lowercase. Since my debugger is case sensitive. To show all the words, some of them are lowercase, in lowercase. New words I had tried to define in bytecodes. Comma, immediate, and compile only. The first group. Next, LED low turns on LED. There are two subroutine calls to push value onto data stack. The same function could be extended by LED on. That's only a simple program in bytecodes without subroutine call. And the wait is just to run empty for next loop. For example, 9 wait, that would be 10 times. And the cmove will call C function directly, the strncpy. Should be more efficient, much more efficient. Then debugger just go into debugger. 11 new bytecodes are defined from hex 43 and up. New bytecode I've tried. Call return. Do byte constant push to data stack. Do H constant push 16-bit value. Do T constant that put 24-bit small integer to data stack. And hex 47 just cmove. And 4.8 is comma. And 4.9, that's branching, query branching, conditional branching. 4.8, that's branch. And 4b, do next. And all these are for in bytecode programming. And last is debugger. See, the word compile only using 2 new bytecode. And immediate as well. And comma. The LED set up LED pin using 1 bytecode, new bytecode. And as well, LED off, LED on. Another word, LED low. It's also turned on LED, but using subroutine call to put the 0 and pin number to data stack. Here is the word wait. Run empty for loop in bytecode. Here is the word cmove. Just using one bytecode. That will run C function. The word debugger. And this could be a little bit complex. Blink. Lots of bytecodes used. To blink LED n times. The n will be on the data stack given. Using tools, even design tool, is important. We are tracing, debugging, and testing. I've learned first redefine column words in bytecodes. Define subroutines in bytecodes. Redefine bytecodes to call C function directly. But the words defined in bytecodes could not directly call other words. So, not directly calling to just the CFAs, but directly calling to subroutine at CFAs instead could improve system even more. Could be my future work. That's it. Any questions? Yes.
I have a suggestion. If you have an ISR that's running about 100 hertz, then you could redefine weight and do multiple things.
Well, I'm sorry, I'm not sure. What do you mean?
Well, if you have an ISR, interrupt service routine.
Oh, interrupt.
Interrupt, yeah.
Oh.
That running at 100 hertz, then you can redefine weight. It's just a counter, and then you can do multiple things, multitasking.
Yeah, right. That's another future work, I think. Mm-hmm. Yeah, very important. Yeah.
Future, yeah.
Yes. Okay. Yeah. Okay. Thank you.
this. All right, everyone. I'm Brad Nelson, frequent speaker on topics related to Forth Haiku, amongst other things. Today I'm going to talk about the latest feature I've added to Forth Haiku, the ability to let it see. So just for some quick background, for those that have managed to miss all of my prior talks, Forth Haiku, the idea is to have tiny programs in a dialect of Forth that are translated to JavaScript and from JavaScript to GLSL shaders and to do beautiful things with them. And the notion is there's a website that you can post your programs, and you can edit the programs of others and produce all kinds of interesting art, and now interactive art. So the basic idea is that we've got sort of the typical core Forth word set, but the words that we provide do work on floating point. That's primarily a concession to JavaScript living underneath, and also the nature of what GLSL shaders are good at. And the idea is that you have these tiny programs that are basically being run once per pixel in the image. And on GPUs that are available today, that means massive parallelism, and it means you can do all kinds of fun things quickly. The basic idea is that in addition to the core words, you've got an X and Y position, and that lets you know where you're at in the image and how things are being rendered. And then at the end of each run of the program for each pixel, you're supposed to have a red, green, and blue value, and optionally an alpha value sitting on the stack. And this lets you take a very pithy program like this, quite literally a haiku, you know, the 5, 10, and 5, and or 5, 7, and 5, and get an image like that out of it. I find that sort of thing exciting and fun. Over time, I've expanded the set of words, and particularly because the words particularly because these programs are being edited online, I need to be thoughtful about what I add, because I have a compatibility problem. Folks are submitting haikus and changing them, and if I break them, if I change things out from under them, old programs don't work. People's expectations are violated. And the other constraint is that I'm forced to work within the limits of what WebGL can do. I'm trying to do this on the internet, and so WebGL is my conduit to the outside, and so its peculiar limitations are the constraints I have to work with. And then the other thing is I don't want to have a huge vocabulary. I don't want to have a word for every little thing, and so I've tried to keep the set of words that I add, or the clever feature-specific words to a minimum. So places where this has worked really well in the past with animation, I added the word T for time, and that just magically allowed things to be animated, all kinds of fun possibilities. I used a time in seconds since midnight because I could do clocks with it. So you could get fun things like this where it shows the actually local time. One of the things I started doing at some point is highlighting the particular feature set that the haiku is using with an icon in the corner. I recently went through a change to make the animated haikus a TV set rather than a video camera, because that was rather confusing, now adding the ability to do video, as you'll see in a second. I've been astounded what people have been able to do, especially just with that time word. A small program like this turns into something amazing like that I would have never guessed people would be able to do in that small a number of lines of code. And I do appreciate tremendously the folks that submit the sundry haikus that are far more clever than the ones I've come up with. One of the other things that's been relatively successful and with a small number of words is interactivity. I introduced circa a little before last ForthDay MX and MY for the mouse X and Y position, some words for buttons. Those I'm a little sad that I had sort of duplication of reading an individual button versus several. It's a mixed bag. But it lets you do fun things like this one where you've got the mouse cursor and you can move it around and have the haiku react to it. So good fun there. Audio has been an area that's been a little bit challenging. Audio is hard because you put a random spray of color on the screen and it's not going to, it may not be the most beautiful thing, but it's not going to be painful. Whereas sound, if you get it wrong, it can sound dreadful. I've tried several different things here. I've never really been fundamentally happy with audio. One of the early things I did was
audio based on the image from the corners of the image, and then doing something with a pentatonic scale to try to, sort of make sound to match the image. It was sort of a mixed result. Later added raw audio so you can actually emit the waveform, but that's challenging because, again, it doesn't take much to have it sound bad. Just to give you a sense of what this can work like. Oops. So you can do interesting things, and or combine it with. But it's pretty, as you notice, even this, there's lots of little clipping sounds and whatnot. So in any event, audio continues to be a fun challenge. But for this time round, what I wanted to explore was video input. And of course, as usual, I'm limited by what I can do with WebGL. But the basic notion is that the video feed coming in would be available as a texture. And that allows for some interesting possibilities. So surprisingly, despite all the things that are visually going on in the haikus, from the point of view of WebGL, this is the only geometry that's being rendered, two triangles. And what's happening is that the rendering pipeline in WebGL is assembling these into a set of fragments, and then all the fun in Forth Haiku is happening actually in what's called a fragment shader. The WebGL is able to take user code in two forms: a vertex shader that is able to manipulate geometry, and a fragment shader that works in the texture space of the image. And up until now, one of the things that I haven't been utilizing is the fact that GPUs have this fun texture unit that's able to have one or more textures streaming in, and you can sample from this at various locations. I've just been doing calculations to produce the image, and so this is sort of opening up a new avenue. One possible area of future exploration, obviously, is that vertex shader that I'm not making use of. So, hinting in the future. So I've added two words. One of them is sample, to sample the image, and it takes an X and Y coordinate and then just returns the RGB values in the stack. And this means that a very simple haiku give you an image. I very quickly discovered that it's convenient to have a black and white single value sample, and so I've got a special or custom word for this that just returns the properly balanced combination of red, green, and blue, because there's enough places where you just want to look at the brightness level of the image. And so this lets you do all kinds of fun things. I'm going to, at this point, jump over into the actual Forth Haiku site, because it's simpler to go through there, and just give you a fun sampling of the possibilities. So you can do fun things like this, where you're both transforming the coordinate space and sampling the image. You can do interesting combinations. It's easy to take, well, that doesn't show up very well on the video screen, but you can combine existing haikus and overlay them and mix them with video in various ways. You can, of course, do all kinds of interesting transformations of the image to get funhouse mirrors and this sort of effect. And you can also try interesting things like, here's my attempt at a dither. So you have a very low-res version of me. Oh, I just lost this microphone. And another fun category of thing that you can do is, let me find the, you can do, whoops, not do that. You can do edge detection. So here's a fun one where I'm doing edge detection and then also overlaid on a background of that's been pixelated. So all kinds of interesting highlights. And here, for example, I'm taking multiple samples from the image, slightly offset, and subtracting them to accomplish that edge detect. Yeah. And let's see, various cutouts, all kinds of possibilities. So I encourage you to take a look. One of the other fun things about it is that it does work in a variety of places, and so it's obviously with a webcam, but you can also do it on your phone and this sort of thing. So that's all I've got. Any questions?
Yes. So, can you print your extraction?
Go stand over next to him so you can get it on the internet.
Indeed. I will stand next to you and talk to you.
Can you do like feature extraction, like say that's a car and that's a house?
So one of the unfortunate challenges is because I'm working at the end of the WebGL pipeline, I can do a lot of operations, but ultimately I'm doing them at once per pixel, and so I have very local information. Unfortunately, there are ways to at the end of that go through and combine things, and then that would sort of lead you in the direction of being able to do more advanced things. But you're heavily constrained, at least in this environment, in terms of how much aggregation you can do together of the image, and that in turn limits being able to do something very elaborate like an actual image detection algorithm.
It would be kind of like writing an application on top of what you've done.
Yes, but again, the challenge is that it's sort of the GPU is taking advantage of massive parallelism, so it can be done in general. In the constraints of the Haiku environment, you don't quite have enough rope to combine information from neighboring pixels to be able to do this. So you're forced to do very local calculations.
Yeah, that would be more of a local app than a web application, really.
I mean, all things are possible, and these days, especially, there are all kinds of opportunities to do computation on the client and on the web. But yeah, challenges abound there. And yes.
So there's no way to census your neighbors.
No, unfortunately, you can redo samples from your neighbor. So you can query and say, I want the pixel from over here and the pixel from over there. But unfortunately, you're making that decision without any information about what happened in those neighbors. So there's no, the sort of the only point of communication is that texture coming in, and there's no neighbor-to-neighbor communication. The underlying system has a variety of options there, but it's not cleanly exposed in a way that you can use currently in Forth Haiku.
Your image is not a good data store.
No. Yeah, exactly. The closest you can come, for example, to a blur is take a bunch of samples and hope that you've gotten enough of them that it kind of looks like a blur, but it's not covering every pixel and every, yeah. So.
Plug the shirts.
Well, so while I'm up here, we have these lovely new Forth FIG shirts, and there are all sizes available in the back of the room. They're $15 each, so if you like a shirt, come on back and we can hook you up.
And if you're out on the web, you want one, what do we do?
You can send an email to me, so.
Or the list.
Or the list, or just make some noise, and we'll get to you eventually. So.
Contact somebody. Well, even though my email is all over everything, I still get people that say, "Oh, I didn't know what your email was." It's a break. Now is the time to order lunch. Dave will give us some words about that. If you don't order lunch now, you're going to be hungry. So make sure that people on the web aren't ordering lunch.
Well, there may be interest out there.
Yes. Find out what you're going to be eating.
Okay, so this year we're having lunch delivered from the treehouse, which is normally the place that we go to have our food, but we're going to have them come here this year. And in order for us to tell them what we want, I've made this convenient sign-up sheet. So they have pizza, and then I've copied the entire menu down here. If you don't want to have pizza, you can choose something else. So if you want a pizza slice, just check off up on top. If you want something other than pizza, your name and your request down here. And sometime later this morning, George will call us in, and it'll be delivered to us. Okay, any questions about this? Sam?
If we do not have cash on us,
We're good. You're good.
we're still good. Okay.
Apparently.
Is
So,
there anyone that doesn't have cash on besides? Okay, you're good too.
okay, so please take note of how much your item costs, because we're going to need money from you. Yes. That's what? Ecogenic. No carbs. There are. You can make a request that instead a hamburger on lettuce and without the bun or something, or just don't eat the bun. Okay, that might be the easiest thing. Okay, don't make it too difficult for them. Okay, I'm going to start. What?
Can we have the drinks in his
Yeah.
icebox?
We have drinks here. Kevin is going to put the drinks on ice around now. So we have Coke, root beer, 7-Up, Diet Coke, and what else? And water. Yeah.
7-Up, Diet root beer, Diet Coke, regular Coke.
Okay.
Okay.
Dave, are we going to be eating alcohol? Are we going to be serving alcohol, or are we going to be serving it here?
I think we'll have the food delivered in the hall and come in here to eat, or you can walk around, whatever. Yeah. All right. So we have T-shirt sales now. Andreas has some Forth books. So please take this opportunity to talk to one another.
What about we put our initials on the menu so that when the stuff comes in boxes, we initials?
Okay. Yeah, I can have them do that.
How did that happen?
It gets goofed up sometimes.
Me too.
So now if you put this, if you do it, just hit the
Down button? Run away. And everything will be happy again. Can we make these a little dimmer? I noticed that the screen looks to me kind of washed out, but.
Kevin? Excuse me, how much is the water? I mean, you're a speaker, right? Yeah. Free. Okay.
See that one there? That's cold water. And then the warm water is over there. So help yourself out of a blue cooler of one cold.
How's that?
That's awesome.
Sign up. No, we're passing it around. I'll take it.
I want that you will make more presentations through the year so far as notes. Or I want that when that that you use the narrative on the screen as a backdrop rather than read it. Just tell us about it. And I mean, it's really hard to do.
By email.
No. I mean, as you're talking, instead of reading what you have, and it's a difficult thing to do. The fallback option is always just to read it there, but gradually, I hope that you'll become comfortable with describing to us why this is happening, how you arrived at this, and so on. Just prepare, and as you're preparing to talk.
This is my verb.
Yeah. It's what's
Verbatim.
Yes, very good. Well, it's Latin, so by the way, it's very phonetic. So as you practice, maybe as you practice presenting, when you rehearse it before the meeting, just think about
Why?
the story. Yeah,
Story.
And we love stories.
Okay.
And especially when you have, some folks have really small print, you have good big print. That's very important. Because we're old. And so, yes, thank you so much. All right, well,
Pay after you eat.
This is the fourth countdown, and then it's these 7 segments for Earth creation.
Sorry? Oh, I don't know. I think it's Kevin's laptop. I've never asked.
It's probably an app.
Probably.
It's a challenge to solve.
There's a lot of work in this school. A lot of interesting papers from 2019. But still, I wanted to see how
So there's, supposedly there's HDMI, but I don't know where to plug it in. I brought this cable.
Well, there is. Okay, we've got that coming in. Try plugging that in. We might have to disconnect this for a moment and let it do a scan.
And I set it up for set it up for
There you go.
Okay.
You're in.
Awesome.
You're on.
All right, thank you.
Yep. Good test. Do you have audio at any point?
No.
Cool. Then that's all you gotta test. You'll be fine.
Thank you very much.
Yep. Not a problem. Switch back there.
I'm hoping this goes less hassle-free than my previous 2 presentations. Being here is going to help a lot.
Murphy is in charge.
Yep. We'll see what happens.
Most of the time we do perfectly fine, but like at the moment, I have a spot on my camera that I can't get rid of. Of course. Something always happens. So, we're set. Good.
boundaries of what can be. So you just know how to do something. Doing marketing is stuff. So
One minute warning.
Well, I have already sent just there is a video comes over USB over it's how you debug an Android. Wired down here. That's an It's just Paul Hardy. Hey Paul, where are you?
Right behind you.
Oh, you're all set to go. You're 2 steps ahead of me.
Not yet.
Display is up on the screen. If you want my advice, I recommend you put your
Oh, I was just going to do it like this.
and do it like this, but
Oh.
it's up to you.
I think I'm okay. Nothing. If I don't trip over anything.
Says. Paul, he's okay.
Famous last words.
You see that bucket of money that's on the table by the coffee? Yeah.
That's fine.
It's fungible cash.
much more complicated than it gets.
How many IQ tests can I fail?
You can just.
Is this your spigot? You want a little extension cord?
No, I got plenty of power.
All right then. You can plug in here if you care to.
Why not?
Are you mic'd up?
Am I? Can you tell?
Yeah, you got a mic. Okay, great.
Can you hear anything electronically?
No, I've got it here. Yeah, I actually monitor the sound.
Okay.
Start talking about stuff.
Testing 1, 2, 3. This is a talk about PDP-11s and Forth and stuff.
Do you use Arduino as well?
No. PICs. You know microchip PICs? This is for old time's sake.
Okay. We're about ready to start, so grab a cup of coffee. We're underperforming on coffee consumption, so get on it. Yes, underperforming on coffee consumption. So have a cup of coffee to work up your energy for more coffee consumption. Sit down, be quiet, and let's listen to our next speaker. I'd like to thank Leon for subsidizing the coffee. Thank you, Forth Incorporated.
Leon made a request that everybody use the microphone.
Okay. Testing 1, 2, 3. All right, my name is Paul Hardy, and I started using a PDP-11 when I was a sophomore in high school. I had access to an IBM 1130 my freshman year running APL, and as an Algebra 2 student, the power of APL was completely lost on me. But I fell in love with the PDP-11. It's what made me decide that that's the kind of stuff I wanted to do when I grew up. So for years I'd wanted to resurrect PDP-11 FIG Forth, the standalone version, and earlier this year I finally rolled up my sleeves and did it. But the standalone version runs on a floppy disk, which has limited space. So the next logical step was to try to port the standalone version to a larger disk. The original FIG Forth floppy had 70 Forth screens, 70K. I recreated what I think was as faithful a reproduction of the original floppy disk image as possible with 70 screens. Then I came out with another version with 150, and I realized a lot more would be nice. The RT11 file system allows up to 32 megabytes on a partition, so I figured some kind of disk with that kind of range would be nice, no more than 32 megabytes. I settled on the RLO2 for one very convenient reason. Another reason is that it was contemporary with the release of FIG Forth. Tech introduced it in the late 70s, I think 1978, and it had some nice features. By that time, Ken Olsen had decided he was going to move away from support of the older 18 and 36-bit computers and focus on the VAX line. The older disk drives for the PDP-11 had these dual compatibility modes for the older 18 and 36-bit machines and the 12-bit PDP-8, but not the RLO2. It was designed just as a disk drive for the PDP-11. I kept the RT11 disk structure, the file system, exactly as it is on the floppy disk. Usually on a hard disk you have a lot more directory entries, but I wanted a gigantic Forth.dat file for screens. So also I wanted the Forth.dat file to start at exactly location 16,000 octal as on the floppy disk. I wasn't sure if doing otherwise would get me in trouble at the time, but it seemed like a good idea. So Forth.dat, I gave it 8 megabytes, 8,192 screens, and Forth.mac is the assembly language for the core of Forth that boots up, and there are a bunch of other files after that. So one thing to note about this, Forth.dat starts on the 7th kilobyte on the disk. So here's a 16-bit word that describes the position on the disk, and this was the clincher for choosing the RLO2. Exactly 10 kilobytes are on a track, so exactly 10 Forth screens. You don't have to go from one track to another if you're scanning a screen. It's all guaranteed to be on the same block. There's a 9-bit cylinder. The 15th bit can be set, so you have to use a double word in FIG Forth with a high word set to 0. And there's a 1-bit head, upper and lower, 6-bit sector. The Forth.mac file has lines that will compile for various operating systems, RT11, RSX11, and, most important of all, the standalone version, alone equals 1. So in John James's original code, if you set alone equals 1, it compiles for the RX01 floppy. I added a new definition for the RLO2. If you set that, the RX01 support is not included, but RLO2 support is instead. You only have about 7.5 kilobytes that you can fit into the core. So you've really got to be parsimonious about what you put in there. And on the RX01 version, I did not enable the extended instruction set. The original didn't. With the RLO2 version, I figured why not have a hardware multiply and divide capability built in instead of taking extra time performing those actions. So the first thing I needed to do was make sure I could actually boot off the thing. I decided the simplest thing to do would just be to print a greater than sign and halt. I wrote code to do that, and it worked. So once I had that working, it was time to load the binary Forth executable that's compiled for the RX01 floppy disk version. And that worked. So at this point, I'd figured out how to move the read-write head around and read the sectors I wanted into the right locations of memory and boot the RX01 version of FIG Forth. There's still no support in this for the RL02. So the next step was to add RL02 support. RL02 again is the hard drive that I selected. So FIG Forth has this word r/w, and PDP-11 FIG Forth has a different version for RT11, RSX11, and the standalone version. I needed to write yet another version for the RL02. And the syntax is very simple. You just give it a memory address, a screen number starting at screen 1, and a flag for read or write. Inside the Forth assembly file, there are 3 words that can call read write, and the only one that's used by other words in the assembly file is buffer. So if you do a list or a load, they're calling buffer, and that calls read write. So here's the inconvenient thing about the RL02. You can't just tell the controller, I want you to go to cylinder 5, head 0, sector 4. You've got to see where you're currently located, know where you want to be, calculate the relative offset, and then tell the controller to move the read-write head by that relative offset. And it's not even, say, a ones complement offset. You've got to give it an absolute value in cylinders and then a direction bit. The controller had very simple electronics on it. So the first thing I did, since Forth.dat starts so conveniently right on a kilobyte boundary, the 7th kilobyte, I had read-write just add 6 to the screen number to get the absolute block number on the disk. I figured that would allow me to have an infrastructure for access across the entire disk later on, including the operating or the RT11 directory structure in the beginning. So I do that, and then RL set is the thing with RL in case it was possible support for another drive in the future, but I anticipate that happening or being necessary. In step 2, the block number, that 16-bit cylinder RL header, asks the controller to find out where it's currently located, and that'll give you the current cylinder head and some random sector on that track. So at least you know what sector you're on. RL diff calculates relative difference and seeks to the new location. And from there you can read or write, whichever block you're interested in. Here are all the words. So I got all this stuff working. RL status, RL error is an error message if there's an error reading or writing. And as I mentioned earlier, I wanted this infrastructure to be available for the entire disk, so I added a new word called absolute read-write, and then read-write just added 6 to the screen number, and that became its only job. Then it passed everything along to absolute read-write. So with this absolute read-write word, someone can access the directory structure at the beginning of the disk, and even the bad sector map if desired. And it worked. I got what's now FIG Forth 1.3.3 to boot and load, and I'm going to show you a live demo of that. It might be hard for me to hold this mic and type at the same time. Okay, I'll try. So yes, I admit it. I wrote C code to create the RT11 disk structure. And I'm going to do a make disk clean. I'll show you that there's no disk in this directory, and then I'll create a disk and I'll boot from it. I'll say one other thing. You can see a bunch of files here, like the LDA absolute loader file and LST files. I compiled them under RT11 version 4, and they're in the distribution so that if someone doesn't have RT11, at least the binary files are there for you. If you have RT11, you can recreate them yourself. Okay, so nothing up my sleeve. I will just type make. And with all the, you have almost 2 megabytes still available in the RLO2 after the 8 megabyte Forth screen file. So I stuck these other files on the disk. You have the macro11 source, the listing output, the RT11 command file to build it, the bootstrap code for the RLO2, a no boot that I put on a blank disk, and I converted the, I typed in John James's original Forth manual in LibreOffice about half a year ago. And then I took this and did a plain text export and massaged the text and created this guide.txt file that's also on the disk, and a glossary, the FIG Forth glossary in plain text format. Okay, let's see what happens. I'm using the SimH PDP-11 simulator here. Actually, let me first show you that. Okay, so we have 2 disks there. There's a blank disk for playing around, experimenting, and the FIG Forth disk. So I'll boot off the FIG Forth disk. So these messages, whoops, these messages are the same as what John James's original FIG Forth printed out. The string extensions is something I put together for a dump word. FIG Forth has dump, and John James gave a dump definition in the user's guide, but there wasn't a dump already in FIG Forth for the PDP-11, so I wrote one. And I also wanted to add to it capability to convert to and from ASCII and radix 50 for handling the RT11 file structure. Here you can see the basic Forth stuff. There's Bill Ragsdale's editor, an assembler that John James wrote, and string routines that John James wrote. So there are 2 empty screens, and I wanted to see if I could fit the dump words in there, and I did, and it's dense code, I'll warn you, but I'll let you see it. This is mainly the radix 50 stuff, screen 18, and then screen 23 is dump that uses the screen 18 stuff. Actually, don't worry about the radix 50 code, but I'm showing you this line for a reason. Here's a sample of John James's assembler. I wanted to swap bytes, which you'll see why when I run the dump, and I took the definition. I used the word from 479 for that. So code starts a PDP-11 assembler definition. Here's the name. S refers to the stack pointer. Parentheses are an indirect. The convenient thing was the PDP-11 has a single assembly instruction that will swap bytes called swap. And the instructions are given with a comma after the end. And then you end with next comma and C semicolon. Then here's screen 23, the dump stuff. And dump word is in line 13. And most of the stuff happens in dump cell, which prints out 1 line at a time. And I'll give you a real quick example. The binary image is loaded starting at location 1000 octal, and the beginning contains some constant definitions, some global definitions. The Forth dictionary starts around location 1050. Here you can see the literal definition and then execute. And this prints out a 16-bit address, 16-bit value. The bytes, the PDP-11 is little endian, so this is the low order byte and then the high order byte. And I flip those for the ASCII output. That's what the swab instruction was for. And a radix 50 decoding, which means nothing in the Forth dictionary, but it would mean something if you're manipulating the RT11 file structure. And notice these two lines. This is next. Next on the PDP-11 is only 2 words long. Very efficient. Okay, I'll switch back to decimal. And another thing I did, I keep seeing messages on news groups and lamenting about not being able to have a Forth interpreter that can that someone can use to play with the original starting Forth book. So I added some words to allow that. And they're here. I was almost done writing this stuff, and this document that Bob Smith had written fell into my lap from the Netherlands Forth group. And I wrote to him, I told him what I was doing in FIG Forth. I asked him if he would agree to let the document be placed in the public domain so that all of FIG Forth could remain public domain, and he agreed. So here's his stuff, and then my stuff. So the one thing I've used from this, notice also you can type for get starting. So if you want to experiment with the starting Forth book and then flip do that. The one thing I've used in this is the page command. Real simple. So that's most of what I want to show you in this version of FIG Forth. Let me show you now the RT11 file system. So I'm booted off an RT11 version 4 disk right now on an RK05 disk. I'm going to get a directory listing of the FIG Forth disk that I created.
BT52, all right.
Yep.
Those were the days.
Yes, they were. Here you see the FIG Forth disk. It's got a volume ID of Forth 1.3.3, the version. The owner is FIG, and the files. For the creation date, I used the date of the listing file for PDP-11 FIG Forth. And if you look over here, you'll see that the files are copied, and the block sizes even match. Actually, let me show you a quick example of using FIG Forth. I'll switch back to the other disk. Oops. I also added a backspace support to FIG Forth, by the way, for the second RX01 floppy. So here's an empty screen 8192. And Bill, I hope I haven't forgotten how to use your editor. It's been several months. Oops.
How big was the FIG editor? 3 screens?
Oh, you're still in colon.
Oh, geez. Yeah. Okay. What have I done? Oh, I exited the editor. I'm sorry. I have forgotten how to use the editor. Sorry. Anyways, there's screen 8192. Here are credits. Here's possible future work. There's something else I want to show you towards the end. Future work, I want to support more than one RLO2 drive, and the controller will support up to 4. I'll probably support 2 drives as a start. I also want to try to add real-time support to FIG Forth. And the RT11 file system, there's a 7-bit year. The RT11 directory structure actually lets you specify that there are extra words. I might try to add something and see if it still works under RT11 version 4 to let you have years that are many thousands of years into the future. And the PDP-11 and FIG Forth are really a match made in heaven. They have a common 16-bit architecture. There's a very powerful Forth for a standalone PDP-11 implementation right now. The PDP-11 assembler is an extremely powerful macro assembler. And as you saw, next is only 2 instructions. However, the PDP-11s are a dominant, but I think simulators are going to be able to let PDPs be experienced by people many years into the future. The PDP-11, I think, will always be around for a long, long time as a simulator because of its history with Unix. And now there's a version of standalone FIG Forth for the PDP-11 with a large screen area. And here are the resources. We have the main stuff is on the stackosaurus.com website. This is all the same as in the last presentation.
You might want to mention that your slides are going to be up on the SVFIG website.
Oh, my slides will be up on the SVFIG website. And they are already up on my website, which I'll show you. So there are 2 kinds of word definitions in the macro assembler file. There is a 2: definition, and here's an example. Here's the read-write word. So all it does is add 6. So up here, you have, in the red you have the Forth code, and in the blue below you have the actual macro 11 assembly code. And you see how the macros just invoke Forth dictionary words. Swap, lit, 6 plus swap, and then ARW. You can't have a slash in a macro 11 name, so the names are changed a little bit. And then you end with the semicolon. The other kind of word definition, well, one other kind, not counting things like constants or that sort of thing, is a pure PDP-11 assembly language word, which you need to access the disk controller. You know, this is for an example, getting the status of the disk controller. Wherever I could, I used plain old Forth. So here's the website, stackosaurus.com. Here's the main page, and if you click on the FIG Forth link, you get to this. And if you go to this table, here's the RLO2 bootable Forth image. Here's the blank disk. There are other RLO2 blank disks out there. Use this one if anyone wants to play, because this has the small directory structure of the FIG Forth boot disk. And then I have some files here for convenience, but they're also on the PDP-11 disk. The macro 11 source listing file. After typing in John James's original guide into LibreOffice, I converted it into plain text. And so there's a copy of that on the RLO2 image. And I also converted the glossary. I put it in LibreOffice and then converted it to plain text. So there could be a plain text version on the RLO2 floppy. And all the corrections, I went over the FIG Forth stuff with John James, got his approval. I went over the glossary changes I wanted to make, got Bill Ragsdale's approval. So I think this is an official version of FIG Forth. Thank you very much. Are there any questions? Yes?
Is there a PDP-11 VHDL or Verilog core that you can actually use this with?
So the question is there a PDP-11 VHDL core or something like that? And the answer is yes. I should have mentioned, actually, on the website, I give instructions for using the SimH and the ERSATS 11 simulators, which will run on various operating systems. There's also a PDP-11 core for the, it's something like the 1134A, maybe the 1144, I forget, and it has RLO2 support. And that was another motivation for adding RLO2 support. It does not have floppy disk support. The floppy disk is a real pain because you got to deal with sector interleaving and skewing between tracks. The RLO2 doesn't have any of that. You know, it's very straightforward. So I think adding RLO2 support is going to further enable people to experience this in the future. So. Question?
I just wanted to mention that there are perhaps a dozen or more processors available to this day that use pretty much the same architecture. It was widely imitated. Many of those have FIG Forths and other Forths.
Widely imitated but seldom duplicated.
Yeah.
All right. Well, thank you.
You want this? No, the HDMI. Congratulations, you're all signed in.
Is anybody not on the sign up list that wants to? Paul, have you signed up?
Where is the DisplayPort adapter?
We sold it on eBay.
What did you get for it?
I've left it there, but maybe I just decided to
There.
grab it because
Yes,
I failed
sir.
the IQ test.
Thank you.
We're planning on having dinner at Su Hong this evening.
Which
so
one?
Think about that while you're thinking about anything.
Are there still two of those?
Su Hong? Yeah,
Yeah.
there's at least one. Yes, it is towards Sunnyvale. He's no longer with us.
Testing one, two. The first year I had an iPhone, we went to Su Hong Bistro for dinner, and I asked Siri for directions to get there. And Siri drew a map all the way to Pennsylvania and started giving me directions. Turn left on Santa Teresa Street and go 1,080 miles.
That's right.
And my relationship with Siri has stayed pretty much the same since then. Well, let's start this at the beginning. So, my name's Leon Wagner. I'm with Forth Inc. I've been programming in Forth since 1982. I've worked with Forth Inc. since 1984. I've been an employee since 87. And I took over the company in 2006. And so people ask all the time, what are people using Forth for? So I want to sit down. We have several large commercial and industrial applications that are actually going things right now. And so I'm going to talk to you about 4 of them. The first one is Logix Controls, which is industrial refrigeration control systems. There are 3 kinds of refrigeration. There's the kind you can reach into, the kind you can walk into, and the kind you can drive a truck into. These systems are for the last one, the kind you drive a truck into. Very large-scale refrigeration plants. The second one I'm going to talk to you about, I've spoken to you about for the last couple of years. It's an ongoing thing. We've done some great new things this year. The Radius Labs RL8200 antenna control system. New customer to us. We've been working with them for about 2 years, StimWave, and they're doing wireless spinal cord and nerve stimulation for pain management. For those of us who are getting older and have bad backs. There are days when I've worked so long on this project, I just wish they would shoot one of those things into my back. I could use it. And the fourth thing I'm going to talk about is Schweitzer Engineering Lab's ICON optical network multiplexers, which are used in the power industry. They're used to tie together power substations. And each of these affects your life in a different way, even if you don't know about it. The logic system is very much a part of the food chain. Most of the food you get that's refrigerated or frozen has a Forth system controlling that to keep it cool or frozen. So Forth is feeding you. The Radius Labs RL8200 control system, antenna control system, and its predecessor made by a different company, the 7200 control system, are used in every single satellite Earth station. So anytime you do anything that bounces off a satellite, watch TV, listen to the radio, use the internet, all of those things have Forth in them. Someday, if you need to have pain management using the stim wave system, there's Forth in that. And the Schweitzer Engineering Labs and its predecessor from GE, the optical network multiplexers that tie together all of the power substations. Anytime you turn on the lights in North America and they come on, say thank you, Forth, because there's Forth in that. So the first one we'll take a quick overview is the Logix control system. Do we have a laser pointer? Sorry for asking so late, after I need it. Without pointing, the blue boxes on this screen are control panels. They have embedded Forth systems in them performing local control over the network.
Green button there.
Okay. Ah, nice. Is that it? So there's one. A couple there, out there on the compressors. The PCs, represented here by laptops, can be running a Windows Forth system that's doing the actual control and monitoring status of this system. So, let's go on. So the various pieces that are in there. The SVFIG for Windows GUI application does the real-time animated refrigeration graphics. I have a sample of that coming up. Network and remote internet access, automatic alarm and failure, and remote notification. They can send texts to people that something's going wrong, or send emails to them, or even call them on the phone to tell them that something is going on. Trend logging and reporting for monitoring temperature and equipment status and so on. And there's an equipment maintenance manager, various diagnostic tools, and they put their entire operations manual and documentation online so that they're visible from any of their PC-based stations. This is an actual screen grab of one of their systems. This is written in SVFIG for Windows. And this is animated. When you see this in real life, it is really cool because stuff's moving. Even the fans move in the graphic. Very nice. All of these are customized per system. So they have an artist who does all the layout and so on, and then ties all those graphical elements into their control points and monitoring points in the database. The control panels that you saw back here, those blue boxes, are the Axiom 2 control panels. They're all implemented with SwiftX ARM for embedded Linux applications. Each of those boards is running an embedded Linux with a BusyBox on it, and we're running within that environment. They use a PC104 bus-compliant board stack. They have a bunch of communication devices, Ethernet, because everything is connected together on the network, on the local network. There's a telephone auto dialer in case they need to call you up and tell you something, which I think is cool. Optically isolated serial ports, because yes, the world still uses serial ports. And the usual digital and analog I/O points for control and monitoring. This is what one looks like. In the upper left-hand corner, there's the CPU board stack. The CPU board is on top. These should look familiar too, a bunch of optically isolated inputs and outputs, power supply, and so on. So those are used to control down on the plant floor the various pieces of refrigeration equipment. Next up, Radius Labs. I talked to you the last couple of years about this antenna controller we've been working at. So from the top down, we have the SVFIG for Windows GUI application, which is the antenna control unit touch panel control and status. That's the part that's the most visible to the customer. We have a SVFIG for Linux cloud server application running as a cron job on one of our cloud servers that does daily Intelsat ephemeris updates. I'll take a little side trip here. We implemented NORAD 2-line element set tracking this past year. I'm sorry, pointing, not tracking. We're not following it. We're just pointing at it. We use the ephemeris calculations to figure out where to point at something. And then we just keep recalculating and pointing at it. So the 2-line element sets have been out there for years and years and years. And if you look at this, this is just a whole bunch of the records. And every day we just refresh a copy of this from Cellestrack, and then we serve it up to all of our antenna controllers. And if you look at the format here in the columns, can you see where this came from? Dave? Punch cards. Yes, sir. There are 70 columns here. So the format is the name on its line, that's line 0, and then lines 1 and 2 contain all of the various ephemeris data and identification data that are updated more or less daily that let you point at any of these named satellites. So for every geosynchronous satellite that's up there, there's a record in this file. So there's about 7. What was that? No. That was weird. I just lost it.
Oh, you got to sign back into the Wi-Fi.
Oh, is that what that was? Okay, it just timed out. Okay. Well, anyway, we don't need that example anymore. That file contains all of it. The next thing we had to do was the Intelsat version of this, which is IESS, based on Intelsat's station standards. And there's one called IESS 412. And it gives an 11-body set for ephemeris calculation that's very, very specifically for geosynchronous objects. The TLEs, you can point at stars or whatever, they're a little less precise. So 2 of the big satellite operators, SES and Intelsat, use IESS 412. And so when it came time to do it, I asked them, where do I go to get the download of all of the parameters for all the satellites? And they said, oh, you just go to our website and download the satellite you want. And I said, no, I want all of them. It doesn't exist. Instead, you go to their website, go to the pull down, select the satellite you want. It gives you a text file. You download the text file, and the text file looks like this. And it's the content of what is essentially formatted as an email. Dear station operator, here are today's ephemeris data. So I wrote a program that runs in SVFIG for Linux that runs as a cron job, and every day it goes out and it pretends to get the pull down at every one of these web pages, downloads all the text files, and then munches through them and pulls out all of those data. And when it's all done, we have a CSV file with everything in it, and then all of our antenna controllers just download the CSV file and parse it and pull out the data. So that was kind of a lovely little kind of side trip to go on for an application that we use for a Linux SVFIG. The same program also actually runs on the Mac SVFIG because they're virtually identical. The other thing the Radius antenna controller has in is a whole bunch of ARM Cortex M4 microcontrollers running SwiftX ARM, and they're doing all the motion control, position feedback, and the button UI on the front panel. Oops, no, next. So the ancient history part. This was the original Vertex RSI Model 7200 ACU that a bunch of people at Vertex plus me helped develop back in the early to mid 1990s. There are thousands of these out there. That company was acquired by General Dynamics. They discontinued the product, no longer support it very well. And so one of the people from that team reconstituted the original brain trust and got us all together, and we built this, and this is going to be the new gold standard. There's already quite a few of them out there. It's been out for about a year, commercially available. And it's a considerable improvement. The UI is a touch panel that's running SVFIG for Windows. And the button interface that you see on the front panel to actually do physical motion of the antenna, there's a little Cortex M4 microcontroller sitting behind there, plugged into the network inside the box. handling that. Out at the antenna, there's a big box called the drive cabinet. It's got a whole bunch of Cortex-Ms running SwiftX in it, doing the actual motion control, moving the antenna. That's fun. So it handles all the motor control, the motion control, and then there's a position feedback from encoders and resolvers. Those are all handled by some SwiftX programs. That button panel you see up on the right, it has a little CPU board behind it, and it is taking care of all of the local motion control and giving status on the motors. Here's an actual antenna installation that I went to just a couple months ago. This is at the SES South Mountain Earth Station, which is in Somis, California, just south of here, north of LA. You can see we were just hooking it. Everything is with extension cords. So right there is that drive cabinet. And so it's permanently mounted there. Not so permanently mounted, there's the antenna controller standing on a plastic table, hooked up with a long extension cord. That's ultimately going to go in that shelter, air-conditioned shelter over there in an equipment rack. Next up, this nice company in Florida called StimWave, who make this pain management system. There are 3 components to it. The Freedom microstimulator is the actual implant that goes inside the patient. That is a hugely blown up picture of it. It's only a few centimeters long. Each of those dots you see along the left side are the 8 electrodes. There's also a 4 electrode version. Each of those electrodes is 3 millimeters long, and the space between them is about 4 millimeters. The electrodes are connected to, in this central core here, an ASIC. And the ASIC is also connected to a little dipole antenna. And all of this is implanted inside the patient's body. It's extremely thin. It's basically injected into the body the same way you would put a microchip in a dog. So the old way, this isn't really new technology. The old way was you would have something quite a bit bigger than this. It would have a wire hooked up to it that would go to a great big battery pack, and the patient would have major surgery, and the battery pack would be implanted in the patient just above the hip, and the wire would run along the spine until the place where the electrodes were placed. In this case, the surgeon just places the microstimulator with a small incision in the patient and basically drops it in with a 10-gauge needle. It's pretty nice. The other nice thing about this, their stimulator, is that it's okay to keep it in the body during an MRI. And the old ones that had so much metal in them, you'd have to go through major surgery to have them removed if you had to have an MRI. This is a big consideration for the kinds of patients that need this sort of thing. So that's part 1. Part 2 is the wearable antenna assembly. That has 2 parts, an antenna and a microwave field stimulator. And the MFS portion is the part that has Forth in it. It's running an MSP430. I'll get to more about that in a few seconds. And then the third part is how you program all this. And they have a program called Wavecrest that runs under iOS, typically on an iPad, also possibly on an iPhone. And there's a subset of it that runs on the Apple Watch. And that's used by the clinician, typically a doctor who's programming the device. The microwave field stimulator, okay, that thing looks like it's as huge as a battleship. It's really, this is it. The part that has Forth in it, there's an MSP430 right here on the back side. And that's running SwiftX MSP430. It has a Bluetooth low energy data interface. That's this big monster here. That's for use with communication with the iOS device. It's also used for various kinds of debugging functions. I put a Forth interpreter on here that you can connect to over Bluetooth using a little Bluetooth terminal application that one of the iOS guys wrote. So it's pretty cool. There's a microwave transmitter, but at the top there's the power amplifier right there, and that goes off to the antenna. Along the way, we monitor it for both forward and reflected power, which is interesting. There's a JTAG debug and programming interface. Right down here, these little pads, you plug in a little plug and nails, and you've got a JTAG interface. That's what I use when I'm doing the program development. So my SwiftX environment is interactive with this device via that little JTAG module. It also has USB charging and an optional serial interface over there on the side of the board. You almost can't see it. There's a little USB connector on the edge. You see it? It's a micro USB. That's how you charge it. And it also, as long as it was there, we put a serial port on it. So we can use that as an alternate connection to do communication with the board. It has an I2C fuel gauge and a real-time clock on it. The fuel gauge is so we can very, very, very accurately monitor the charge and discharge cycles on the batteries, so we can be very smart about charging it and using the power. And it has a really simple user interface for the end user, the patient. It's 3 buttons and 3 LEDs, and I couldn't get a picture of it, but I have one here. It's this. There's your whole user interface. It's got an on-off, it's a little membrane, sealed membrane switch. It's an on-off button in the middle, a plus and a minus. So plus to turn it up a little bit, minus to turn it down a little bit. Both of them at the same time to change programs. There are programs stored by that iOS application. What was that? Oh, okay. That's almost starting to get my attention. And there's also a piezo speaker for audio feedback that's tacked to the back side of the board. And there's a picture of the Wavecrest programming app. It's just a typical iOS GUI app that the clinician uses to set the parameters. So the fourth thing I want to tell you about is the Schweitzer Engineering Labs ICON system, Integrated Communications Optical Network. This is used in power substations, and it passes SONET, synchronous optical networking rings around between the various substations. This is just a typical add-drop multiplexer. We're adding and dropping channels in the SONET, carrying all kinds of information, Ethernet, digital I/O points are carried back and forth, DS0s and DS1s, a lot of legacy communication interfaces because stuff in power stations has to last for hundreds of years, so it's all old, and we have to be able to carry all that traffic. The most important things that we did in the implementation of this system were passing precise time distribution around the optical ring for use by synchrophasers so that the power stations have all their timing synced to do the correct kind of failover so that the grid doesn't go down. Our requirement for precise time distribution was that we had to be less than 1 microsecond off from the PPS signal coming off GPS. And we actually got it down to 100 nanoseconds, which was pretty nice. So we beat their spec by quite a bit. The last thing that we added to this system, so most of this development wrapped up in 2014. The last thing we added was anti-spoofing for the GPS. We used the GPS to derive the PPS for precise timing. Just as we had completed this and it was going to market, somebody posted a YouTube video showing how to spoof GPS. And if you were to spoof GPS and get this thing to think it's a different time than it is at one of these nodes, and that node timing was being used to synchronize, the grid would go down, or that portion of the grid would go down. So we came up with a scheme to have the capability of many nodes supplying the GPS, and a scheme that they pass back and forth to keep that information synchronized in such a way that if you were to try to spoof it, you would have to spoof all of those distributed stations at the same time in the identical way in order to mess up the time. And that is so close to being impossible that you would just say that it's impossible. It would be extremely challenging to do that. So this is an important security feature that this system has that the other systems don't have. The inside, all the Forth in it, if you look along the slots here, the only one of these, every single board that's in here except the power supplies and the blank slots, have microcontrollers on them. Each of these little ones, so there's 4 microcontrollers right there. There's one there, one there, one there, one there. Each of those is running Forth, except for one, which has a Xilinx microblaze in it, and it's running the network management interface, which was written using the Trex stack, which is written in C. But everything else is Forth in here. And it's all using our SwiftX for the cold fire. We also wrote some command line interface programs in SwiftForth for Windows to provide Flash programming utilities for factory setup and testing. Very simple. And coming right up, we're just starting this now. I just met with them and we started the first of the implementation. Their next generation is going to use a dual-core ARM Cortex R5 in a Xilinx Zinc UltraScale Plus chip, which is an amazing part. And we're just in the middle of implementing that right now. This is a block diagram of the UltraScale Plus, the CG series, and it has a whole bunch of cores in it, plus a whole logic and other things. This little block right here that has a dual-core Cortex R5 is where we will be living. So that is where SwiftX ARM will be running. The block up here with 2 or possibly 4 Cortex A53s will be running an embedded Linux, and it will be running the network management and again the Trex stack for SNMP. And then all the rest of this is just various kinds of glue. Some of these things we interface to over the bus. And then programmable logic, that's where all of the Sonnet stuff happens, all of the proprietary stuff to do the add-drop multiplexer and the various things happen in there. I think, yep, that's all I have. We've been busy. Yeah. Thanks. Sean,
next to the question.
why don't I just repeat the question so I don't have to run around the room? That's okay. Just say it and I'll repeat it.
Okay. You're using the Zinc 720?
No.
No. You're using...
It's a CG series. It's maybe a CG9.
Oh, okay.
John is asking which of the Zinc series. It's the Zinc UltraScale Plus. This is new.
Yes. You're not using any of the boards from Avnet, are you?
No.
Very good. The reason being is they are of very poor quality. I worked at a place where they had one of those Avnet boards, X-rayed, and the solder joints, you could see voids in them.
The board that we're using is the ZCU102 from Xilinx. It's as big as a battleship. It's an enormous board, and it's not a very good board either.
Yeah, but you do have you do use a good board vendor to create the boards.
They're just from Xilinx. I don't know who makes them.
Okay,
Yeah.
well,
It doesn't matter. We're just using that for the evaluation board. The actual customers' boards they manufacture themselves, and their boards are phenomenally good.
okay.
Yeah. Yes.
On the 3-button thing, how does the user know what program is being run? Is it ping alert?
On the 3-button interface, how does the user know which program they're running? The middle button has a green LED under it. Oh, I didn't mention the LEDs are yellow, green, and of course, blue. We use the Bluetooth typically the blue LED to indicate the Bluetooth status. The green tells you what's happening right now. A single blink, it blinks in a cadenced way. A single blink is program 1. There are 3 programs. A double blink is program 2. A triple blink is program 3. And a long and a short blink means I don't know what program it is because you've changed some settings and haven't saved it.
So this is a real user, or is this like a clinic?
No, this is the actual end user at home, the patient. Yeah. Dean. Yes. The question is, do we use the coordinates of the receiver? For the PPS function, not the actual time, for the PPS function, we are distributing that around the network, and then we do something secret to it. Yeah. That's the proprietary part that we developed that makes this system special, that we're giving accurate time distribution across a very wide, potentially very wide geographical distribution of these nodes. And that's why you try to distribute the GPS points.
You're fighting Einstein.
Yeah, sure. Yeah, I know. Yeah.
And so my question really gets down to, are you attempting to have a simultaneous idea of time?
Yes.
Okay, which means
within 100 nanoseconds.
Virtualized to some physical place.
Indeed.
Okay, so
Yes.
all of them are actually stamping that time.
Yes.
Okay.
Yeah.
Thank you.
Yep.
Yeah.
Anything else? Okay, we're done. Yes, dual mic. This is the pointer.
Green button, okay. Hello, everyone. I'm Andreas Wagner, and this is about parse time execution, which is not unlike compile time execution, and also not unlike reader macros, according to Sam Falvo. And so this came out of my desire to make use Forth for general purpose computing. I'm not sure what that means, but I don't like the term general purpose computing in this case because there's no such thing as really truly general purpose problems or solutions. And so I changed this to a problem of unplanned spontaneous computing as an alternative problem to solve, because it seems to be a better, more specific problem to solve. So Unix is thought of as being good at spontaneous unplanned computing. You can pipe some text to unique. You can unique it. You can sort it. You can join it. You can doesn't matter. You can do anything with it. Unix commands tend to be filters. They are based on function composition, and they separate data from code. You have flat, dead ASCII text piped into commands, and it plays well with others. It's ecosystem oriented, and so Unix commands have one-off disposable interactions in a way, but they have complex code. The code behind these commands is rather complex, and whereas in Forth you have more disposable, shorter code for more specific interactions, and but if I were to use Forth as a general purpose system as a general purpose tool, such as a bus pirate or on my PC even, that would take quite a bit more effort, I would think. And but Forth systems tend to be rather self-sufficient, and whereas Unix systems are general purpose, they are oriented around an ecosystem more, whereas Forth systems tend to be self-contained and for single-purpose embedded use, for a single-purpose and deeply embedded use case. So if I want to use Forth for some more unplanned computing or spontaneous sort of interactions, more like a UI than a programming language, I would want to have more random access over the problem and solution. I'd want it to be better at filtering, I would think. So when someone asks me how to parse a CSV file in Forth, I often tell them that they should use the comma compiler, because in Forth is not about filtering dead flat text. because in Forth, I think Sam Falvo said this. I'm not sure. I think it was you. You said this years ago. He said in Lisp, code is data. In Forth, data is code. So we have to keep that in mind in our solution as well, so we don't just recreate Unix and the potential problems that come with it. So in Forth, I keep in mind that if data is code, well, then I guess it would be code, right? So in my Forth, the welcome string gelforth is the same as reset, warm or cold, and there is no OK prompt. I just use the new line character after a successful computation or execution of the code. And if something is unrecognized, like an unrecognized string or something, it just gets compiled. The comma is, of course, the parentheses are, of course, recognized. That just drops the string that you compiled. If something is partially something with it, if part of it is defined and part of it is not, then that's sort of a defining word semantics. So when someone asks me how to parse, so then that person tells me that their CSV file looks like this. It has no spaces between the commas and fields of the CSV file. So I'm forced to tell them that, well, Forth only comes in words. Yeah, so sometimes what I need to parse is beyond my control. Non-Forthers have designed a format, which happens a lot, and the external natural world beyond the microcontroller sensors may not have been written in Forth, and yeah, so the natural world was not written in Forth necessarily, and what this means is that what you need to parse may not be, it may not be your fault, or it may not be in your control, but it is your problem. Insurance companies call this the act of God insurance policy. And so parsing, it's not your fault, but it is your problem. And so I thought, well, a seismograph has readings that need some interpretation, to my understanding, as a non-seismologist or geologist. And it's not just a flat literal. And I wonder, well, non-textual sensor readings are data. Shouldn't they also be code? So then I was reading this Reddit post. You don't have to read all of this here to have on a slide. But he just explains why compile time execution makes the compiler so simple, the compilation so simple and Forth. Compile time execution opens up the compiler to factoring, and by having code executed during compilation, you can, during compile time, you dissolve the compiler into factors that mix with your code. And I wonder, what could this idea behind immediate words also dissolve parser complexity? Because as it is right now, I feel parsing is rather complex in Forth. Sometimes I have to do it. I usually try to avoid it, or do it as early or as early in the process as possible, rather than like buffering everything and doing it offline. I usually try to do it as early in the stack as possible, and as little as possible. Sometimes I have to do more of it. So my keyboard is a user interface for interacting with the Forth interpreter as a user interface. The keyboard interfaces with that interface. My mouse is also an input device. Could my mouse also be writing code as well? And could the seismograph be, could this be the name of a word, rather than having some text that describes it indirectly? Could this reading from the device be the word name? And so then I was reading this article by, I think, Daniel Ehrenberg, I think. I might have gotten the name wrong, but he said pattern matching can be viewed as the inverse of functions. So to match, if you have a number and a number that is twice the size, if you want to match a number that is twice the size of another number, you could do 2 divided by equal. And if that's true, then you would that would be a match. And he does all sorts of interesting. He has all sorts of interesting examples in this paper where he has examples of unit conversion and matching XML documents and stuff, XML features and stuff like that. And this also implies applications to reversible computing. You can go both ways, compute both ways with this potentially. So then I thought, well, could I put rather than having an ASCII string header for each word, could I just put code in place of the header? If I want to just match a literal string, I could use the same word or compare to compare the string. And what this does is it dissolves the outer text interpreter into it dissolves the outer text interpreter into your code. So it opens up the outer interpreter to factoring and decentralizes it as well. So then I thought, well, this would mean I could do stuff. I don't know if this is something I'd want to do, but what I could do is I could match a 32-bit number to determine which fetch or store word to use. So I wouldn't need to have a typed operator necessarily. I could do this. So I wouldn't need the typed operators. And so in this example here, the tick still gets the execution semantics of something, maybe not a word, but something, as in the case right here where it gets the execution semantics of doubling. And not literally this, but just doubling, more abstract than that. And I typically write my headers to be non-destructive, but I have been thinking about doing otherwise. So far, I've been just using non-destructive headers that do not destroy the data that they try to match. But for reversible computing, that I may want to have the body non-destructive as well. So so here you need to be mindful of the scoping. And if you use a dictionary for pattern matching like this, you need to be mindful of the scoping that sometimes. And Mark Smith came up with a rather cool idea of fetching the scope of a word and storing it into the scope of another word, or saving the scope of a word and storing it into the scope of another, and compiling it into another word. Because with hyperstatic scoping, the previous words are shadowed by redefinitions. And if you can save the previous scoping and use it somewhere else, that would you can build all kinds of things with that as you like. And it makes this helps with this problem. And thank you. Here's an example of here he describes how the bind word works and how you can fetch one word and store it into another effectively. But too much text for a slide. So thank you. Any questions? Oh.
So I noticed when you first described the concept to me, I thought that it was very similar to List's reader macro. But now this, and it's something very different. Like, how do you see this being used in the future? Like how does this help you deal with unplanned computing?
I can. There's some examples I forgot to show. Oh, just one moment. So it helps. So basically, with with random access. That's the HDMI. Yeah. So. Maybe. Okay. So the dictionary is sort of a random access over the solution space, or the problem. It gives you sort of a random access, and you can do things like you can, in this example here, you can fetch the execution semantics for byte-wise for matching bytes, basically, because a lot of words will depend on that, and you can store it in the execution semantics for matching cell 32-bit numbers, because a lot of words depend on that, and in that way you can basically convert a 32-bit system into an 8-bit system just by fetching the 8-bit semantics and storing into the 32-bit semantics, and so on. Yeah, were you gonna say something?
What's the book of the month?
Book of the month is this.
How much is it?
I don't know. I guess $10.
Okay. Is there a list available on the web?
There's on the svfig.github.io. There's a link to the list, the gallery, but not the full list.
The meeting schedule.
The meeting schedule, yeah.
Okay. Pretty much everything's $10 plus shipping.
Yeah.
But you're here now. You don't have to ship it.
If you're here, the shipping is 0. Yeah. Oh, here's the mic. Second mic.
This is all sorted it out afterwards, and especially I'd like to thank Andreas, who adopted the whole project and accepts with good grace all my silly ass suggestions and advice. And just keep in mind that none of it should be taken as orders or direction or anything like that. It's all his. Introduce yourself, Ting.
Okay, this is Chen Hansen Ting, and I think I would take another subject than Forth. D-loop in mitochondria. So this is very interesting for you all programmers. And the first thing is all life forms were poorly designed, okay? Including you guys, everybody. But I should have been more and say that all life forms were poorly understood, okay? Because too many compromises has to be made to deal with many different external requirements for life to exist. Okay, plants were much better designed because the external constraints are much less stringent. Okay, they were designed to acquire energy from sunlight. Okay, and they do not have to move. So that's a much better requirement to meet. Okay. Oh, sorry. Animals were much more difficult to design. okay, they have to acquire energy from food. They have to eat, and food must be digested and stored away. And when they have to be used, food, they have to move by burning stored nutrients for energy. And the animals have to be self-sufficient. Okay, they have to move and they have to stand alone. So to support movements, we need respiratory and circulatory systems, and mainly they require using the oxygen. And oxygen is required to produce energy in a form. But oxygen is toxic. Okay? So that makes things much more difficult. And the animals were designed to deal with the problem with two very interesting cells. You have to have lots of red cells, and the red cells are sacrificed to carry oxygen to other cells. So the red cell is very interesting by itself. It doesn't have a nucleus. It's produced there just to be sacrificed because it has to carry oxygen, and oxygen is toxic. So eventually oxygen killed the red cells. And the red cells have to be regenerated to keep the life on. And the other, at the end of the energy chain, there are mitochondria. They are incorporated into the cells to oxidize nutrients to produce ATP, which provides energy for all the other components in the cell to survive and for animals to move. So mitochondria is a very interesting small thing. That's the subject of this talk. But mitochondria is part of a cell. Okay, it utilizes oxygen diffused into the cell to produce energy. But mitochondria cannot catch all the oxygen and use them. So there's bound to be oxygen escaping from mitochondria, and this oxygen has to be neutralized by vitamin C, which is another of my favorite topic. Okay, so let's concentrate on the mitochondria. Mitochondria is the smallest endosymbiotic organism required by all cells. It is part of the cell, but not a cell itself, because it has its own DNA. It has its own DNA genome, and its DNA genome is inherited from mother. And its DNA genome is independent of the nuclear genome. But the nuclear genome and the mitochondria genome seems to be able to cooperate to achieve to support life. Okay, so mitochondria supplies energy, but the cell supply lots of proteins that are required by the mitochondria. And mitochondria is very interesting in that it has only 16,569 bases. So that's the smallest freestanding organism that can divide. Okay, so this is one of the simplest life form. or the simplest life form, although it depends upon the cell to carry out much of its functions, but it is genetically independent. And this too, my interest in mitochondria is that it's the simplest organism which can reproduce itself. So if we want to understand life, you better start there, okay? Because are at least 10 times or 100 or 1,000 times more complicated. So if you understand the process involving in life, this is the first thing you have to understand. Okay? So this is one picture of the mitochondria, which is, I think, less than, it's 100 microns or something. I don't know. It's very small inside the cell. But it's very interesting. It has outer surface, and it separates itself from the cell. And inside it has lots of another compartment which has folded surface. Okay, the surface basically occupy the entire volume of mitochondria. So it has a very large surface area. So, and on this surface area are the mechanism which converts food into energy. So when the oxygen diffuses into this mitochondria, it has a sufficient, very large surface area to catch the oxygen and make use of it. Okay, so this is basically how mitochondria is designed, and its only purpose is to catch oxygen and burn food to convert the ADP into ATP, and ATP will be utilized by all the other parts of the cell to carry out its own functions. So mitochondria, it has 16,069 bases, and we understand most of it. It encodes 37 genes. 13 genes are for the respiratory complex. This is the complex which utilize oxygen and burn glucose or fat. And there are 22 genes coding for the transfer RNA, and which has you must have to produce to build proteins from amino acid, and 2 exogenes for leucine and serine, and 2 others for RNA. So we understand most of the code in mitochondria, and one mitochondria inside its folds contain 2 to 10 copies of DNA. So the DNA is not like a nucleus containing a nucleus. It's contained in the fold, but it can have 2 to 10 copies of DNA. It have to have at least 2 for division. Okay, but it may have many copies. But why? Well, we don't know. But this is what the mitochondria is. The mitochondrial DNA is a circle. Okay, and it has 2 strands. there is an H strand and an L strand. It's a heavy strand and a light strand. They are complementary, okay? And the N strand contains lots of G base, and L strand contains lots of C base. So they can be separated very conveniently when you analyze the DNA. And so most of the genome, as you see, encoding lots of proteins, and these little rectangles are the tRNA. They encode 22 different. They are used to synthesize protein with amino acids. But on the top of it, there is a region which does not encode the protein. And this is called the D loop or the control loop. And it's interesting that in many of the electron microscope images, this part, most of the other part are double-stranded, but that part was triple-stranded. So the two H and L strands separates, and another piece which is complement to the H strand was created. And so on the top of this this D loop, it forms a letter D. Okay, so it has 3 strands, and this part does not encode any protein. And I believe this part contains the secret of life. And this is how mitochondria function. The basic thing is how does it construct itself? How does it divide? And I think the information must be contained there, but because there's nowhere else. And I thought that since this whole thing is 16,000 bases, and this D loop is 1,122 bases. So 1,122 bases. That's a little bit more than 1 block of Forth code, right? So we've been dealing with the blocks of code all our lives, okay? And I think if information is in that block, I should be able to look at it. I may not be able to understand it. At least I can look at it to see what's in it, okay? And it's only 1 block. We have, many of us have experience of reverse engineering somebody else's code. So looking at 1K of code, whatever, we can do it, okay? So
Sorry,
that's
sir.
what, yes.
Is that a picture of the end through a spiral? Is that through the spiral, or is that a spiral wrapped around an
It's
actual
a circle.
loop?
It's a circle. The DNA, the mitochondrial DNA, it is a circle of
Of strands. So that
two strands, two complementary strands. Okay. Okay. So it's not difficult. Okay, and that's why I decided to look at it. Because that's within my 3 billion base pair for a human. It's too big for me. Okay. Only recently we can put everything 3 billion base pair on a DVD. Okay. Okay, so look at the mitochondrial D loop, the little stretch which does not contain any information to produce protein. So 1122 bases. It's divided into 3 sections: the left section, the central section, and the right section. And the central section is called conserved block. And that's the block which contains code. Okay. The other 2 sections, left section and right section, there are information in them, but really variable from species to species, from individuals. But the central section, which is only 309 bases, this section is conserved over all species, and so the left section contains some information about termination association sequences. This is the D loop, when it replicates the small stretch, it always terminates there. And the conserved sequence block on the right section, there are many points which starts the D loop, the stretch. Okay, let me just show you some picture of it. So the genome of mitochondria was completely decoded in 1981, way before the Human Genome Project, because it's the smallest genome. Okay, and so many species have been studied. And here this is from a paper in 1997, and the investors analyzed many mammals and found that they all have different genome, different D loops, but this central section are all conserved. Okay, and in this region there are 3 points which basically starts the replication of this D loop. And here these 2, and this one is basically terminates this small stretch of D loop. So I believe that this section, all the other sections seem to be variable. Okay. But this section is conserved, and this contains the essential information which enables mitochondria to survive and to develop. So we can, because of this central section, here are all the code. So 1122 bytes from that yellow line to this point. And this is what I call the left section, central section, and the right section. And this, the red one is the termination associated block. And this is called conserved sequence blocks. So basically, when you build a new D loop strand, it separates the genome separates out, and it replicates this area. And so I try to so these are the markers, the function of the regions. Their function has been identified. Okay, this is the function. In the prior one was from a paper in 1997, and in 2017, if you look at the data called the MitoMap. And they have identified a lot more things in the area. And this point is called the OH. It's the origin of heavy strain, origin of H strain. So basically, when it replicates, when the whole thing replicates, it starts from here. It goes around, and there is another point called the OL, the origin of L strain, which is 2/3 around the circle. So when it replicates here and go around the circle, and when it hits 2/3, it hits the OL. And the OL, when you replicate to the OL, this strand continues replication, and the OL, the L strand, starts replication on the other direction. So it goes, H strand goes from here around the circle, and on the 2/3 of the way, the L strand starts to replicate. So here are many things we understand. There are more detailed functions, but this whole area, the function, except this one, the function of in the central area is not very well understood. Yes.
I found a capital A at the in the line 241. Capital A, is that special?
Yes. I think that there's capital A, capital C, and I think these are they have sequenced many people, many different species. So there are modifications, and some of the modifications were indicated by capital letters. Okay, and I think that in 1981, when they first sequenced the first mitochondria, and then they start to a lot more people are doing it. And finally, when the genome project, or the NIH, the entire genome project, when they started, and they found that the original mitochondria was from a black person. And I think people feel very uneasy about it. So the current one, this is in the reference Cambridge database, okay, and they switched to a Caucasian, okay, for whatever reason. I think they have made the wrong choice. They should have sequenced a Chinese for the standard. But anyway, the conserved species difference are in the right section or left section, but central section are conserved. They are all the same. So how would you look at this piece of code? Okay, and one way of looking at it is from the genetic code. We know that the AGA encode for a particular protein, ACA, and all this called codons, and 3 bases encode 1 protein. So most of the other areas, when they encode proteins, they have these triplets, and they have all the triplets have been identified. So to know that okay, this stretch is encoding certain gene. So and this is the red. These are called the start codon, and the green ones are the stop codon. Okay, so these are generally, if you are coding for proteins, you have to start with a code this, and it has to be terminated by a code like this. So for no good reason for it, I just say, well, let me see what code are these in this stretch, and mark the start codon and the stop codons, and it's this way. So from there you can see, well, pretty much random, because it doesn't make any sense. Okay, okay. And it shouldn't make any sense, because this stretch does not code for proteins. So the information definitely is not related in any way to amino acid. So this is what I found very interesting. I was puzzling over it for a year or not. But last month I started to look at the code in detail. So I said, well, one way to look at this thing is to see if there's a repeated pattern in this code. Okay, so I started to do the analysis. I just the whole area. Do the analysis and see if there are repeated patterns. And I'm looking at the longest repeated patterns. If there's any information, it has to be repeated patterns. Okay. So I was import the whole thing, and then I just take about 30. A stretch of 30 bases. Let me see if I can. Okay. Let me try to show you my analysis, or the way I analyze it. Okay. So this way, I just take out a stretch of I don't know, 60 bases, and then just move these 60 base windows over the entire stretch. Okay, so I got 60, and then move one base, so I got all of them in a file, and I put them in the on a spreadsheet, and I do a search. I mean, do the sort. Just sort all these things. And of course, if you sort it, everything will be arranged alphabetically, right? But it's ACGT. Okay, so it's all arranged ACGT. And then from ACGT, I can see repeated patterns. One of the interesting repeated patterns is here. GGGGTA. They repeat twice. Okay. So this is how I do the analysis, the pattern identification. Let me see. Let me go back to my. And I found one pattern has 8 bases. It repeated twice here. And one pattern which has 8, the TGGGGTA. But in here it has 6 G's here. But there it only has 5 G's. So kind of matched, but interesting. And the next one is a 6 base GAC-ATC. So GAC-ATC. So these are the 3 longest repeated patterns. And lo and behold, they all occurred in this region and not in any other regions. So that's the secret of life. What do they mean? I don't know. Okay. Yes. Yes, definitely. This is almost my last couple of slides. Okay. So here, the longest stretch repeated patterns in the central conserved sections are CACCCTAT and GGGGGGTA and GACATC. What I'm expecting here, if this is a code, if this is a program, what do you expect to see? Okay, if it is a Forth program, what I'm expecting is to see call and return. And I'm expecting to see jump and a continuous conditional jump. That's what Chuck told us. Okay, Chuck, you only need these 4 instructions to the transfer instructions. Okay, and in between the transfer instructions, you can have lots of more code. The genetic code, we know in Forth, we talk about the primitive instructions and compound instructions, or low-level instructions and high-level instructions. Low-level instructions, primitives, you have to construct them from the machine. Genetic code, we know the primitive protein coding. It's at the lowest level. There are and protein carry out all the functions. Yes.
The thing about the conserved section that makes the proof that it is key is that if you change any portion of it, it will not replicate because they do not exist. So they are, all other forms of that are deselected. It's the only selected form, so it must be key to the reproduction.
Yes,
okay.
Definitely. Yes, that's what I think this part is extremely interesting. And so, what do they mean? I found 3 patterns. What do they mean? I think from Forth point, it must be something like a call or return, or a jump. Okay. So here is the secret of life. This central conserved section has essential information mitochondria needs to survive. Okay, so it's only 309 bases. Of course, it doesn't do everything. We knew that the mitochondria has lots of information in itself, but it needs lots of information in the nucleus. So it does not have the complete program, but it has an essential part of the program for the mitochondria to survive. And I think the next thing is we need to look up this code in other organisms. In other organisms, in their what we call the junk DNA. The junk DNA are not junk. They are programs. And how they are written, we don't know. But from this study, we have found 3 repeated patterns, which might have certain meaning that we need to investigate.
I don't know if you know the answer to this. One of the things I've always wondered is that the code is being read by a machine that uses it as a formula for constructing something, right?
Mm-hmm. Yes.
How much do we know of the machine itself that reads? I mean, wouldn't that be the place that we'd want to start to figure out the interpretations of these things?
Yes, definitely.
Has anybody written out the molecular structure, the protein shape for the machine that reads these?
Okay.
Boot code.
Boot code. Yes. E-Forth. Okay. Let me see. I think what this is last. Okay. So anybody, any more comments? Any more? Yes.
So, if you think in terms of life in other worlds, so, I mean, there's a lot, it's fascinating what you're talking about, but can this survive in other environments and other worlds that we know of? Like
We know that most of the life form on Earth use this mechanism, okay, but only for energy producing part of the cell functions, okay, and definitely 309 bases does not have the complete information.
Right.
Okay.
But I'm just wondering if maybe that this is starting somewhere.
It's definitely all organisms has it, okay, and this including most of the plants and the bacteria. Okay.
A note from the web, from the stream, is that this is basic protein folding scheme.
No, not necessary.
Okay.
No, the protein is protein. Once you produce that protein, many of the protein fold themselves, and many of the folding have to be assisted by other mechanisms to fold correctly. But this protein is another completely different problem, and this is a genetic program. We are talking about program, okay?
If you took this sequence, have there been experiments taking the sequence into space and bombarding it with the kind of radiation that happens outside the atmosphere? What happens to the? Is there a record of what happens to the change?
This is a very interesting problem, and the people have been studying mitochondria to determine the genetic makeup of people and animals. How do they evolve?
Yes.
And so far we have understood that the life form started in Africa from a single person. Okay. Oh. And this is Eve. Okay. Okay. Eve has this code.
Okay.
Okay. And this code evolved, but the central section remains conserved. Okay.
So a data point that might be relevant towards answering some of the questions that have been posed here. There's a life form called a tardigrade, which is known to survive the rigors of space. So yes, this genetic code will survive in space.
Yeah, tardigrade. Yeah, DNA is really very robust. But this is really an interesting way of looking at the DNA code. We know that it takes 3 base pairs at a time as a codon to make proteins. But you can also look at the DNA as just as Forth code.
Yeah, it's code,
and
machine code.
It's sort of like maybe it's intergalactic message.
Well, we all carry it, okay.
And that's the way of duplicating it.
Yes.
That's how the message is replicated.
Right.
So what the thing is making a quandary.
Wait. Let's move.
Even I can't get to that microphone unless it's here. What makes it a quandary, okay, is that you cannot postulate a way to create this sequence through evolution.
No.
Okay.
No, it has to be designed.
It has to be designed. So you could actually call it God's gift. Okay.
Yes.
Because it had to be created in its entirety, all at once, and in the context where it could be read.
Right.
Okay.
And the mitochondria has to coexist with the regular cell.
Mm-hmm.
And they have to coexist.
In fact, one thing that would be useful, okay, is let's assume that you have a random process that's producing them, and the context in which it can be read is somewhere at hand. So you have this incredible engine that's churning them all out. How long would it have to run? What is the amount of entropy that has been targeted, that has been collected? Okay, what is the entropic probability of it ever occurring? Okay, that's the size of the gift. Okay.
Right. Okay. I think that's all we have, and thank you very much.
Take what you ordered, not somebody else's food. There are 3 tubs. One's all Coke. One's all Diet Coke. One is 7-Up, Diet Root Beer, and water. It's best to take it from the bottom. That's the coldest.
Dr. Tink, that was incredible. It's really
And we'll see everybody after lunch. Thank you very much.